Olá, gostaria de dar algumas informações antes do evento começar. Por favor, coloque seu celular no modo silencioso. É permitido tirar fotos, mas não utilize o flash. Não consuma alimentos e bebidas dentro do auditório. Não acesse o YouTube durante sua permanência no auditório. Ele interfere na transmissão. Se houver perguntas ou comentários, por favor, utilize o microfone. Ao participar dos eventos no CBPF, você permite o uso da sua imagem. Para sua segurança, o extintor de incêndio encontra-se ao lado esquerdo e a saída ao seu lado direito. Bem-vindos ao CBPF e um bom evento a todos.
Good morning and welcome to you all. Now we will have the opening by Professor Gilvan, representing our director of CBPF. Please.
Yeah, good morning, everybody. This is loud. I'm here in behalf of the CBPF director. Unfortunately, he could not come because this week in particular, we have a very busy schedule because of the, we're passing through a process of hiring people, new people for CBPF, and this is very important for us. So he's very busy with that too. But in any case, he apologized for not coming to this event, and he's extending his welcome to all of you. Welcome you, and you probably know that CBPF is the headquarters for the National Research, headquarters for the National Network for the High Energy Physics, RENAFI, and also the Institute of Science and Technology led by Inácio. And this is a very, so this conference is very fitting to our environment here. So I would like to extend our welcome to Rio de Janeiro, to CBPF, and I hope you all have a very good conference, very nice discussions, and welcome all of you to Rio and CBPF. Thank you.
Thank you, Professor Gilvan. Okay, we have a couple of minutes. I just want to do some announcements. So, Wi-Fi you have. The budget, you stay all the time with that because you saw the gates and so on. Outside, of course, you don't need, but entering here all the time. So prohibit bring drinks or food to the auditorium. Okay. Thank you. Yes, and the talks I already mentioned to the morning speakers, but the talk should be sent to Rogério at CBPF and as well as Light-Cone. And if you can, please upload in the Indico page. Unfortunately, this week, the Indico page is having reparation and may be unstable. But please, if you can, try to upload. The posters will be presented tomorrow, start from tomorrow, because today, the place, we have the registration. Now, when leaving for lunch, you should, you don't need to carry your computer and so on. It's more safe just to keep here. This room will be closed after the last speaker and opening again at 1:30. So you can leave your documents. Okay, where to lunch? There is restaurants just close by. At the University of Rio de Janeiro, Unirio, you can find. There are kiosks, and there is a big shopping mall that probably many of you just passed through Rio Sul, that there are plenty of different choices of restaurants, just, I don't know, a couple of meters from here. Okay, just to locate you, where we are here. So this is the Rio Sul. This is about, I don't know, 500 meters. No, and this is where is the other restaurants. You see here, University of Federal do Rio de Janeiro. So you can find some other, but maybe this is nicer. You have air conditioning, no? Okay, remember that we have lunch between 12 and 2:30, so plenty of time to do. Now, certificates will be, and of participation, presentation will be sent later by email, now as well as the registration receipt. Many of you that pay it through the Brazilian Physical Society already have the official receipt, but we are going to make the receipt. Photos will be available in the website, I hope. And the banquet will be in Fogo do Chão, Botafogo, that is quite close to here, no? And this is important. The identification will be picked up with the secretariat on Thursday morning, no? And for the guests, unfortunately, have to be paid by, this is the amount, no? And I hope you are going to enjoy. And please, try to be careful. Move by Uber, that is very cheap, and okay. Now, just for walking close by during the lunch, I mean, if I know that it's very hot, but if you can do it, it's very nice. I mean, you have here the Mureta da Urca, that is just, you see, 750 meters, where there is the famous Urca Casino. Maybe many of you know about the Urca effect, no? And it's very beautiful. I was there visiting. I mean, it's an enjoyable place to go, and as well as to Praia Vermelha, that is 1.1 kilometer. And there is a beautiful path of about 1 kilometer, just on the left side that you can walk. You see many of monkeys and saguis. It's very pleasant. So if you can do. For the others that want to have a nice view during the lunch, but it's not cheap, you can spend about 10 euros or $12 to eat. There is a beautiful restaurant with a wonderful view of the bay that you can come. It's just Terra Brasilis. It's just in this corner. Any question? There is one more thing for the Brazilians that are supported by pelo Instituto Nacional de Ciência e Tecnologia de Física Nuclear. The lady in charge will be here to get your, support during the coffee break at 10:30. So please just go there. Jaqueline, the name of the lady. Okay, that's it. Let me see. Any question? Yes. No? Lowercase, yes. The password, yes, is lowercase. I put in uppercase. It's lowercase, sorry. Yeah, sorry. Lowercase, please, lowercase. Now I notice, okay. Yeah, lowercase. But there is Eduroam as well that many of you probably can connect. Yeah, lowercase. Thank you. So we have a couple of minutes. One important thing. The humidity today is 18%. So please hydrate yourself, okay? There is water just in the left, there is a fountain, and also at the just at the place of the registration, there is also water. So please take care and hydrate yourself. The locals know about that, but you see, this is quite warm, no? So you should take care. Okay, welcome. Take care, please. No, Rio de Janeiro is not an easy place, a trivial place. And please be very careful, okay? I left my personal phone number. I have WhatsApp. I think in one general email I have said, if you need, please call me, okay? Okay, so in a couple of minutes, we start. We just wait if someone is coming, no, and want to. For the moment, thinking. Yeah, for the moment. Yeah, for the moment. Once I asked about full body systems, but I have to check if it will be fine, no? Yeah, I was looking for that. Yeah, for the Zoom. Yeah, someone maybe. Stay with them.
Oh, yeah,
35. Okay.
absolutely.
Okay, so now let us start our workshop. We have the pleasure to have Elke Aschenauer here with us, talk about the electron-ion collider. Please, Elke.
Yeah, so Good morning, everybody, and thank you. And it's my pleasure to come again the second time this year to Brazil, which I enjoy a lot. So I will talk about the electron-ion collider. I will give you a rough idea about the physics program, the accelerator, the detector, and where we stand with the project, and hopefully convince you that it is a project which you have to join if you want to unravel actually the mysteries of visible matter. So, okay, for the people which don't know what the EIC is, the EIC is a high luminosity polarized electron proton-ion collider with a wide range of center of mass energies. What is new and special of it? The EIC is the only new collider which will be built in the foreseeable future, and the foreseeable future is 20 to 40 years. It has a factor 100 to 1,000 higher luminosity as HERA. Both electrons, protons, and light ions are polarized, and we have any nuclear beams which you would like to run. If we compare it to fixed target facilities in DIS, like JLab or COMPASS, we have at a minimum 2 decades increase in the kinematic region X and Q square. And you see here, I will discuss this a little bit more. The EIC, it has an hadron storage ring, it has an electron storage ring, it has a very novel electron injector, and we reuse actually the injector chain which we have existing for RIG at Brookhaven National Lab. Since the science program, the EIC can uniquely address 3 profound questions about nucleons, which are neutrons and protons, and how they are sampled to form the nuclei of atoms. That is actually what the National Academy of Sciences in the US kind of concluded after they did a study on the EIC. So we know how does the mass of the nucleon arise, how does the spin of the nucleon arise, and what are the emergent properties of dense systems of gluons. And then for all the experimentalists also, we built a state-of-the-art detector with a lot of new kind of technologies. So now you could say we have already quite some colliders and machines running. Why do you actually need different probes? And the answer is complementarity, because QCD has 2 concepts which lay its foundation, as you know, factorization and universality. And if you want to test this concept and separate interaction-dependent phenomena from intrinsic nuclear properties, you really need different complementary probes. And these probes are high-precision data from EP, PP, and E+, E-. And if we look, factorization is basically manifest itself that you can write a cross-section by that you have the pattern distribution functions, which you need to kind of measure. You have the hard scattering, which can be calculated from first principles, and then depending on what your probe is, you have hadronization again, which you need to measure the fragmentation functions. So if you do this and you measure, for example, pattern distribution functions, as has been done at HERA, you see here an example and the cross-section which we use to actually extract them. Then if universality and factorization holds, you can really predict your cross-sections from HERA, which has data we're taking at 0.3 TeV, up to 7 TeV at the LHC, and predict very precisely the cross-section. And that works very nicely. But we have a lot of other probes where that is absolutely not yet there, because we don't have actually complementary probes to probe factorization and universality. So what are the different processes which you kind of need for this? And what are their advantages or disadvantages? So you have here hadron-hadron collisions. They are very nice, but the probe has a very complex structure already. So you have 2 complex structures which you collide, so that is hard to calculate. You have no simple access to pattern kinematics event by event. You have a correlation between rapidity and X and PT and Q square, but you get a very strong correlation between X and Q square. What is very good is that gluons can be accessed directly because they enter on leading level into the cross sections, and you can study really nicely gluon fragmentation. So then you have DIS, so electron-hadron collisions, where you have a point-like probe, which gives you extreme resolution, which is very nice. You have high precision and access to pattern kinematics with the scattered lepton, which you detect, and you get that event by event level. And you can separate very nicely, which is also not always easy in hadron, initial and final state effects, because you can do inclusive measurements and you can actually do measurements which have a more complex a final state. And then actually what bridges everything between the two is actually ultra-peripheral collisions, where you have also a photon-induced process. You have, again, no simple access to parton kinematics on event level, but already a bit better because you have the correlation, again, between rapidity and x and the mass of the produced vector meson with q square, and you have access to the initial state actually inclusively. So now if we look to the EIC, the golden process is deep inelastic scattering. I already said it is a probe which has basically no structure, so it provides unmatched precision through the electromagnetic interaction. You have a direct model independent determination of the parton kinematics. So you have your electron, you detect the scattered electron, you have this virtual photon, which interacts with the partons inside the proton. The process is actually basically governed by this equation here, q square, which is the resolution power, is defined by the center of mass energy, x, the momentum carried by the quarks inside the proton or the gluon, and you have y, the inelasticity. And here, some nice animation which we did of such a process where we have an interaction with a nucleus. And then, actually, I said already, the EIC has very large kinematic coverage. The center of mass energy goes from 20 to 140 GeV and gives us access over a wide range in x and q square. And we want to do this because depending on what energy you use, you have access to high x or to very low x. And as you know, the proton actually really changes how it presents itself. At very high x, it is governed by the valence quarks, and then at low x, it is fully governed by the gluons and their interactions inside the proton. So the plan here to actually really imaging quarks and gluons in the proton. So if we start, actually, then we have the parton densities, which we all know, which are basically depending on the longitudinal momentum distribution x, which you have here. But in the EIC, we want to go significantly beyond this. We really want to image the proton in xkt space. And then we want to do the same in spatial momentum space. And then we want to also extract Wigner functions where we basically combine all of it. So the three-dimensional image of the proton in longitudinal, transverse, and spatial distribution. And you would think, actually, why is this something which is needed? And just to give you a nice picture, if you don't have the full picture sometimes, you really get a wrong impression of how things are actually looking. And it's also true for the proton. Actually, if you have the 3D pictures and you really kind of understand how the quarks, the gluons, and so on are interacting inside the proton. So just to give you a couple of examples how well the EIC can actually do to determine these different parton distribution functions. So here is an example of where we measure the CDIS cross-section. So we detect, in addition to the scattered electron, here in that case, a K minus. We do that over a wide range in X. The different colors are Q square. And then we can also bin this in Z, which gives you kind of a handle on the fragmentation. So if you do this, and then you kind of take this cross-section and extract the strangeness parton distribution functions, and you have this here, and here's the impact actually. So before is what we have right now, the knowledge on strangeness, and then the dark curves is after we impact actually the EIC data, then you can see that we will really a very exact knowledge about strangeness, parton distribution functions, and particularly the impact grows with if we have the full energy up to 140 GeV available. But what we learned from that study as well is that if you use semi-inclusive data, so having a kaon or any other final state, which you use in your fragmentation function and PDF extraction, then what you need to do is you cannot separate them out, the PDFs and the fragmentation functions. You really have to kind of integrate them, extract them together, because depending on where you sit, either at high X or at low X, you get the data, your uncertainty is either dominated by the fragmentation function or by the PDF. And to get the best out of the data is actually if you really use both together and do an extraction together. And that is something which some of the fragmentation and PDF groups are actually already starting using some of the CDS data, which is available right now. So then one of the big topics for the EIC, and hopefully finally clarifies the question, where does the spin of the proton come from? So if you write it down, then you know that the spin has a contribution from the quark, from the gluons, and from the angular momentum. So what you do is a key observable is the structure function G1, which you measure for the proton and some other helium-3, because then you have access to the neutron if you want to do a full flavor separation of the quark spin. And then you get actually the total spin contribution from the quarks and the gluons. And if you do tagged asymmetries with pions and kaons, then you can do a full flavor separation for the polarized quark distributions. So here is how well we can actually measure the structure function G1. If you're familiar with the HERA data, it's basically the same plot just for polarized. You see a wide coverage in X and Q square, and the blue bands actually indicate the present uncertainty of this. And then if we take this and do an uncertainty envelope here, so here for the gluon plus the quark contribution in a region of 1 to 10 to the minus 3. And then what is missing here, and that is actually here the orbital contribution. Then you see with the full energy of EIC, which is a dark envelope, you really get a very well determined contribution from the quarks, the gluons, and you see also whether your integral has really converged if you measure down to 10 to the minus 6, which the EIC can do. So I already talked about the imaging of the quarks and the gluons, and that we would like to extract Wigner functions, but that is very hard. So we do first something a little bit simpler. We integrate, we integrate over the spatial distribution, and then we can actually see imaging over the momentum space. And what you see here are examples how actually the transverse momentum distributions of here for the quarks, we can do the same for the gluons, is actually changing if you go from high X to low X. And what you see actually is that the contribution becomes wider and wider if you go to lower X. At least that is what currently the models predict, which are tuned to data which are very high X data from the fixed target experiments. So then we can do exactly the same, just integrating over the transverse momentum distribution inside the proton, and then we get actually the distribution in coordinate space. So here we see how actually the quark distributions, this is the example here is a down quark, changes from high X, where the models predict right now that it sits basically in the core of the proton, and then you go to lower X, where you see that it grows and takes more space inside the proton. And that is also something which we, of course, in high energy collider see, that the proton actually grows if you go to low X. So again, an example why that actually is a very important measurement. And the heavy ion friends in the room here know that the LHC has seen in ATLAS, CMS, ALICE, basically all the experiments, collective phenomena, even in small systems, so in PP and PA. What that means is that you have very long rapidity correlations which go beyond what you have with a dijet, for example. So there have been calculations to this, and one example is this calculation by Heikki and Björn, which is based on a hydro picture and uses fluctuations also in the proton. And what that means is So you have here basically pictures how the proton looks like as function of x for different x and y, and what you see in dimensions, spatial dimensions, and what you see, you have different kind of combinations. So if they want to actually really represent this data, the biggest uncertainty at the moment is how the proton actually looks in a spatial dimension. So are these fluctuations and combinations where you have different hotspots here, for example, at 10 to the minus 3, is this realistic? Or do you actually kind of need to modify the model or the calculation so that you can describe this? And the EIC actually can really map this out. And I show you some example how well we can do that for quarks and gluons. And the example I will show you is for quarks. The process which you use is deeply virtual Compton scattering, where you have your virtual photon interacting with a quark inside the proton. You produce a photon or a shape psi. The quark goes back with a momentum imbalance, and you have a momentum transfer from the incoming to the outgoing proton. And here on that side, I will show you the distribution for quarks. And if I have shape psi, actually, then I automatically access the gluon. And this is what you see here. So we measure the cross-section as function of t, the momentum transfer between the incoming and outgoing proton, both for the real photon produced or for the shape psi. And because a PT squared momentum distribution is, of course, the Fourier conjugate of the spatial distribution. And then what you see here actually is the spatial distribution for one example of x and a q square bin, which we can measure. And you see from the arrow bars, both for the quarks and for the gluons, it's an extremely precise measurement. For people which are interested in the pion clouds, so they would actually manifest themselves in the high spatial distribution here around 1 to 1.6 by a deviation from the models if you have pion clouds available. So we can do this measurements as a fixed q square as function of x, and the same as a fixed x as function of q square. And this is what you see here as an example. I fixed the q square and then I change x, and you see how well we can really measure how the distribution of quarks or gluon changes over the x distribution inside the proton. We can do, and that is something which is extremely interesting for our heavy ion friends as well. We can do exactly the same to image actually gold nuclei. And what we do exactly the same measurement. We produce exclusively shape psi, phi's, or rho of scattering with an electron on a gold nucleus. And then you have the coherent kind of pattern where your gold nucleus stays intact, and then you really image how the gold nucleus is for different x and q square bins. Or you have actually here where the gold nucleus breaks up, but the individual nucleons stay intact, so incoherent scattering, which actually allows you to determine what fluctuations you have in the different configurations of the gold nuclei. And that is very nice. You see here a precision, how well we can do this. We put it in a Woods-Saxon, and that is how precisely we get out the Woods-Saxon if we measure a momentum transfer to the nucleus up to 0.2 GeV. So really precise measuring of really how the nucleus looks like and how the configurations look like. And of course, if you take uranium of nuclei like this, which are not kind of a simple round nucleus, then you will see much more complicated patterns in the final state. So another topic, which is something which very little is known about, pattern distribution functions in nuclei. So the ones from the proton by now, apart from strangeness and so on, we know relatively well. But here what I show you is the ratio between the pattern distribution function in the lead nucleus compared to the one in the proton. that has also LHCPA data included, and the blue curve is actually the uncertainty and the blue distribution. And what you can clearly see is that we know nothing about the gluon in particular as soon as we go below 10 to the minus 2, and we know also not so much if we are at higher x. So we can do a very nice measurement by using the same measurement which is done at the proton, measuring the reduced cross-section, which can be represented by structure functions F2 and FL. Here F2 gives you the quark and the anti-quark momentum distribution, and FL is directly sensitive to the gluon momentum distribution. But the gluon actually in the proton case has been best determined by taking the derivative of the reduced cross-section with Q square. And here you see how precisely over the range in X and Q square we can measure this reduced cross-section. So very precise measurements, and we can do exactly the same for charm, which also is an additional access to the gluon. So if we do this then, and then extract the parton distribution functions here as function of whether we measure only for a squared S below 45 or 90 GeV. So what you see very nicely is, so these bars here represents and the uncertainty, the gray band is what I showed you here as a light blue band. And you can see that down to the 10 to the minus 4, we really can very precisely determine how the gluon distribution looks inside a nucleus like gold, and whether it kind of is different to what we are measuring in the proton. So one of the last topics on the science case I want to discuss is studying non-linear QCD effects. So if we have here the parton distribution functions, then you see, first of all, that starting from an X of 0.1, the proton is completely dominated by gluons. Very often you see the PDFs actually kind of presented that the gluon and the C quarks are multiplied with a factor so that you can actually see the quarks very precisely. So here I plot it really linearly, and you can clearly see that it is absolutely dominated by gluons. So now the question is, and we know from basically the black disk limits that this growth of the gluon cannot continue forever. So there has to be a mechanism which actually kind of tames this rise. The mechanism is to recombination of gluons. As they can split, they can recombine. So if you scatter with an electron of a nuclei, then you basically see at one moment, if you have all this gluon, something like a wall. And then you scatter coherently of this. And so you can define a new quantity, which is this saturation scale, which goes with the gluon density and the radius of the nuclei. And what you see is if you go into a nucleus, you get an enhancement which goes with a to the 1/3 over x. So if you want to really see that this recombination happens, measuring with nuclei is actually very effective, because compared to the proton, a gold nucleus gives you a factor of 200 enhancement in X, where you reach it earlier than in a proton. So there is a golden probe, which we have been using actually in PA. And what it is either dihadron or dijet production. So you see this here, you scatter, you get your dijets, you do this in PP and you do that in PA. And then if you have actually a saturation, what happens is that your backward jet disappears basically, because you kind of get a decorrelation of all these gluons there, and also because of the recombination, you have less scattering centers. So this is something which we have been measuring in STAR with PA, and we can actually here you combine the X and Q square plane with the EIC one. We can reach even deeper in the saturation regime. So saturation happens below this black curve here. And what we measure is that we count these pairs based on what's the trigger. We define a trigger hadron or a trigger jet. And then we look compared in PP and PA how often we have a backward jet. And we did this for aluminium and gold. And of course, aluminium and gold are different, have different gluon densities. And what we see actually here for the red compared to the open is that the gold is actually definitely suppressed if we are in the regime here. And if we go to the higher X regimes, then we see that basically we have the same. And if you calculate the suppression factors, then it follows exactly what the saturation models actually predict. So 1 power to 1/3. The same can be measured at the EIC. And the same models predict we will see a suppression up to a factor of 2. And this is an absolute nice example also where you, because we don't understand a lot about this saturation, where you need different probes to show that you get the same result because of universality in PP and PA as you get in EP and EA. And that is exactly what we expect for the EIC. Then jets, of course, also a very important probe here. And I show you a couple of examples what we can do with jets. So we can study global properties of parton structure, multidimensional imaging of nucleons and nuclei. We can study nuclear effects with jets. And we can, of course, also understand hadronization, which is also very nice. And I give you examples here along of all the publications we have been writing what the EIC can do on jets. So that was roughly the physics program. It's even more richer. I have left out a lot of things. I have left out, for example, the mass, because I know that Senadine will talk about that this week. So the EIC accelerator. It's a very unique machine. It's built onto the, it's based on the RIC collider, which we have at Brookhaven here. We have a hadron storage ring, which can run cis beam energies, 40 or 100 to 275, any energy. The electron machine is 5 to 18. We can run absolutely any nucleus up to uranium, lead, or whatever you want. We have a very high synchrotron radiation power, which limits then actually the luminosity at highest center of mass energies. We have large beam currents, 1 ampere for the hadrons and 2.5 ampere, which is even more than the B factories in the electron machine. The light ions are polarized, the electrons are polarized. We have a very new concept, the electron rapid cycling synchrotron, which is an injector to the electron storage ring, which is actually very important because we want polarization, and that works very nicely. We actually will have new concepts, which are a lot of machines in the future are interested for cooling, which is based on coherent electron cooling. And we have a high luminosity interaction region, which has a crossing angle, which also we use scrap cavities, which is also novelty in accelerator technology. So here I call this my miracle slide of the EIC. So you see the machine, and all of the things which you see around here are things which are new and need to be developed. So you see the EIC really pushes the information on accelerator technology forward. So another important, of course, is the detector. And for that, the experimental program, we had a very active kind of time between 2020 and basically now to, first of all, define really the requirements flowing down from physics into the detector design. And that we have documented in this EIC yellow report. We had a call for detector proposals, a selection of this. We kind of had 2 big proposals coming in, which are consolidated now. We have formed the collaboration in July last year, and now the collaboration is in full action in kind of building the detector. So the EIC user group is actually has a huge worldwide interest in the EIC. We are 1,400 people out of 37 countries and close to 300 institutions. We have been growing continuously. We had actually this year the Poetic Workshop in Sao Paulo, which was a very nice event, which is a workshop dedicated on physics opportunities with the EIC and happens every 18 months roughly. And we had an EIC user group meeting in person in Warsaw. But one of the things which, if you look to the world map, is we would really welcome more collaboration with institutes in Brazil and also in South America. The density on the world map is not yet as strong as we would love this. So I hope you kind of think about whether the EIC is something you want to work on. If we look to the EPIC collaboration, again, we have 171 institutions all around the world, 500 participants. And also there we definitely welcome new groups to actually help us building the detector. So this is here the detector. It's a very compact collider detector, 9.5 meters. We have a large rapidity coverage from -4 to 4. We have large acceptance of tracking detectors, which are equal to the electron and the hadron detector calorimeter coverage. What is, we need high precision, low mass tracking. And that is important because the scattered electron, of course, emits Bremsstrahlung if you have a lot of material. We have novel electromagnetic hadronic calorimetry. We need high performance particle identification all around the detector because we really want to determine pions, kaons, and protons on track level with high precision and low contamination. We do a fully streaming data acquisition. We have, of course, a good luminosity determination, and we need hadron and electron polarimetry. And integration is absolutely the key word here, because the distance between the detector and the first magnets is just 50 centimeters, and that is very, very challenging. So here, just some of the novel detectors which we are doing. I go here from the inner radius to the outer ones. The vertex trackers is built on CMOS monolithic active pixels, ITS3, so very thin. You can bend these ones around the beam pipe, basically like a piece of paper. As the same for the central tracker, we use maps, which are then augmented with micro Arvel and micro megagas trackers. Same at the end cap trackers, we use maps, then particle identification, rich detectors, time of flight based on AC LGATs, which is also a very new thing. And we use novel photon sensors, LAPPDs and IPMs for the rich detectors, which has never been done before. Electromagnetic calorimetry, lead tungsten in the backward direction. And then we have an imaging calorimeter, which is based on Astropix maps trackers combined with a lead scintillating fiber matrix. Hadron calorimetry, I already mentioned the readout in the electronics, and then forward and backward detectors, which I will describe in a minute. So here we have actually in total 23 subsystems in the central tracker. So one of the things is also readout electronics, which we are designing, and we cannot have 23 different chips, so we kind of consolidate. And one of the chips is actually very nice. We collaborate with Sao Paulo to develop the SALSA chip for our MPGDs. The triggerless streaming architecture really provides enormous flexibility, and we will combine that with AI and ML. And we hope that this actually will allow us that our detector is really cognizant and sends me an email and says, Elke, please recalibrate me because I lost my calibration or something else happened. So we have a lot of physics, which I touched on, which requires actually detection of particles at a very small angle, so along the beam line. And that requires that we integrate a lot of detectors along the beam line. And I show you here a picture of how that actually looks. So you see the RCS, you see the ESR and the HSR. And then we have detectors which are integrated either in magnets right after the detector or along the beamline here in both directions to detect this particle. So actually a real integration system, because here it's not every centimeter counts to get this all working together. So the last part I want to touch on is where we actually stand with the EIC project. So it was a long path. We started in 2002 and we finished with the Rilo report in 2021. In 2016, there was a long-range plan, which actually determines that the EIC is the next big construction project in nuclear physics in the US. Then we had the assessment of the National Academy of Sciences on the science case of the EIC, which was extremely positive. I pointed that out already. So in the US, if you're familiar, of course, a project is very structured. And you have milestones which you have to fulfill. If not, you don't go forward or you get canceled. And so the first milestone was CD0. We called them CDs because for critical decisions, and that was that the government basically acknowledged that a new facility is needed. Then the next one is CD1, which you set the cost range and what you're building, and all of this is concluded. And the next big one, the review is actually in November, is CD3A, which basically baselines also scope for long lead procurements. These are items which need a very long time to build, for example, magnets. And that is what we are doing. So it's basically start of construction for some items already. And then a year later here we do CD2, 3 together. So we combine these two milestones, and that is the start of the construction for the full project. And then we need 5 years, and then we go into operations to define the detector. Money is, of course, always a challenge. And in the US, you know, our funding goes like this. It has large oscillations. We have been extremely lucky that due to the Inflation Reduction Act, if you have followed a little bit the politics in the US, we got 138 million just September last year. And that gives us so much money that we can move on a technically driven schedule to the start of construction. And here you see the overall funding profile for the EIC. The total cost of the EIC is 2.8 billion, which comes from the US Department of Sciences. So with this, actually, I come to my takeaway message. I think till today, we have only seen the tip of the iceberg if it comes to understanding protons and nucleons. And with the EIC, we hopefully see the full iceberg. And why is the EIC possible now? Basically, because all stars align. We have the theory developments to really discuss these questions, which I have laid out to you. We have the detector technologies to allow to build a collider detector, which can do the measurements which we need. And we have the accelerator, and that is most importantly, which really can provide us the high luminosity, the polarization, polarized beams, the wide range of center of mass energies in one machine, and actually also have this demanding IR where we have all these detectors and so on integrated. And with this, I would like to invite you to join us. We need absolutely everybody from, if you have friends which are engineers, designers, technicians, absolutely. And here is our lists of jobs which we have. So please apply. And I have sign-up sheets for the collaboration with me as well. Thank you.
Thank you. Okay. Questions to Elke?
Hello. I didn't understand one remark of yours that you said the gluon density between gold and aluminum is different. For me, the gluons are mostly confined inside the nucleons. So
they are different because you have, first of all, a different number of nucleons inside the aluminum in a gold nucleus.
Yeah, but this is not the density. The density is then defined by the volume. You just increase the volume. So the
density is defined, and that is the interesting thing. We have been doing measurements, and we see that if we measure the PDF of gold, the gluon, that we find something different than we see in a proton. So it is not that the gluon density in a gold nucleus is just n times the density in the proton. We have hints, and I don't go back because it's many slides. We have hints that it is modified. You know about the EMC effect, for example, for quarks, which is modified at high X. The same we see at low X, just that it is shadowing, what we call shadowing or a suppression of the gluon density inside a gold nucleus compared to the proton. So obviously there is something going on which modifies the density of gluons in a nucleus, that it doesn't make it n times the density of the proton. And this is exactly what we would like to see. First of all, we want to determine it with high precision. How big is the difference? Because at the moment it allows to 50%. And then, of course, you have in addition the saturation effects, which kick in earlier, which can also modify because you get recombinations. And there is also this naive assumption that the gluon density is completely confined inside the nucleon in a gold nucleus. That's not necessarily true. You have this long-ranging gold gluons which are coming out. And so you have actually more effects which are going on, and that's what we want to measure.
Continuing on this same theme, with high luminosity, it seems as possible you could look at these distributions in different nuclei as a function of X, including going to ratios of X distributions for X even greater than 1. Have you thought about that, or
we
is that?
Yes, we are looking into things bigger than 1. That is interesting. For that, we have to measure at lower center of mass energies because we cannot reach. So if you, I don't want to go. If you look to the kinematic planes, of course, if you want to reach at at high X at a reasonable Q square. If you want to go to Q squared 10,000 or 1,000, you can go to high above, but then you need so high luminosity that it is not exactly. So you go to lower, and then you can go to X above 1. Exactly. Yes.
And I think that'd be very interesting because for a long time, there's been this interest in whether or not only gluons are distributed more broadly inside the nucleus, but also the quarks.
Exactly.
And what kind of leakage or deconfinement or crossover transitions could occur is very interesting physics also.
One of the things is also that you could think of was a nuclear binding happens from gluons which are actually outside of the nucleon confine. So absolutely. For this, I believe the 3D imaging, where you really look how the gluon distribution is modified going from high X to low X, where it sits in the core, more outside and things like this, is probably the even more interesting probe to look to these things.
Shimbo, very short question.
So you just talk about the low energy. So my short question is, so how does your luminosity, let's say, depend on this center of mass energy?
That I can go back quickly. Let me go there, as it's easier to show. So here you have the green curve is our luminosity at the high center of mass. It's limited by the synchrotron radiation because of the 2.5 ampere in the machine. And at the very low center of mass energy, it's actually limited how many protons or nuclei you can confine in a bunch because of inter-beam scattering and so on. But you see that over a wide range, it's basically flat and close to 10 to the minus 4.
Okay, Elke. So we have to move on. Thank you very much.
Absolutely.
Now we have Patricia Magalhães that will talk about enhanced charm CP asymmetries from final state interaction, please.
Thank you, Tobias. Okay, let me just, I'm not very good with microphones. Can you hear me well? Yes? Okay, so hi everybody, good morning. It's a pleasure to be here. Thanks to organizers for the opportunity. I've been here for 2.5 years, so returning home is always great. So what I'm gonna talk today is a little bit about something that we've been doing in the last, I don't know, 10 years. So it's a long history. I try to condensate in the main messages that we've been learning along the way. And so these are my collaborators. So Ignacio, Tobias, they're here, but also there's a lot of work that I'm doing with Jose Pelayas in Madrid. So, okay, let's go on. Okay, sorry. Okay, so I'm talking about multi-body decays. So let's change a little bit the subject. So we're talking about B and D meson decaying into hadrons. So this means that those interactions are sensitive to strong phases. So we can assess the interaction between the hadrons themselves. When we go for data analysis, this means that we can see some of these resonance structures directly on data, which allows us to do spectroscopy. So this is something that LHCb is doing a lot. So every now and then we heard about a new tetraquark or a new pentaquark that's been observed. But we can also study CP violation, and that's my main interest in, so study CP violation. And then we've been building lots of machines, very powerful, and then now we are in a situation that we have access to high data from LHCb, but also from BESS3, and then hopefully from BEL2 as well. And this means that from the theoretical point of view, we have to improve in our models that we are using to analyze this data. So that's the challenge. So CP violation. We have a long history about CP violation. So this is just to put things a little bit on perspective. So we had 1956, the parity violation was discovered. And then since then, we have all the standard model being built and all of this history that you're very familiar with. But what I wanted to call your attention is that the CP violation in beauty was, oops. No. So on the B sector was observed first in 2001, and then only in 2019, so 20 years later, we observed for the first time the CP violation on charm sector. And this was the difference between the two processes that I'm going to discuss in a moment. And then only like last year, we observed for the first time in one decay channel, the first CP violation on charm. So this is very recent history. And there's still a lot of things to be understood. Okay, so I'm also a LHCb person, so I'm a theorist working on LHCb. So the main goal of LHCb is really, one of them is to understand this CP violation signatures. So this is one very striking result. So this is a CP violation from the 4 channels, the B plus going to pions and chaos. And what we can see here is that although when we integrate, so when we add all the phase space, our final ACP is like small, can also be compatible with 0, like in one case, in this case. But we see a giant signature of CP violation localized in specific regions of the phase space. And what I'm going to discuss today is that we understand one mechanism that can explain some of the signature, but there's still a lot to be understood as well here. So we'll come to this later. And on the charm sector, as I told you, so this was the 19 results. So where they observed this delta ACP from D0 to KK minus D0 to pi pi. And this result was very striking by the time, because when we compare with the predictions, the QCD predictions, that they are like light-cone sum rules, these are like 1 order of magnitude smaller. So this opened the door for like thousands of models and people claiming about beyond standard model effects. And this is like very on debate at the moment. And this is just the second result, still not published, but this is just because war and Russia and Ukraine stuff. So these results they obtain by they do a more precise measurement on D0 to KK, and then they use this difference to obtain the first ACP measurement in D0 to pi pi. So the fact that these numbers disagree, like kind of divide the community between the two. One think that this is new physics, and the other thing, the other part, which is where I came from, understand that charm is a very non-perturbative region. So the non-perturbative physics is very important there. So can be ignored. And when we deal with QCD, we have lots of problems to describe these non-perturbative effects. So we have to improve on the theory side. So then, of course, we have three-body. I show the three-body B decays, and then this also have been in the charm sector. There's also like a long search on CP violation on those processes, but so far we wouldn't be able to see anything. But this is on the agenda, and there's a lot of people working on this. Great. So let's recall a little bit when we talk about CP violation. I think this most of you already know, but I think it's very important to recall. This is an interference effect. So to see CP violation, we need some ingredients. And these ingredients are two different paths to the same final state. So this decay we need to have these two amplitudes, and these amplitudes needs to have different strong phases and different weak phases. So when we calculate then the CP conjugate, we will change the weak phase, but we don't change the strong phase. And this is interference when we calculate what we call the ACP, which is the difference between the width of the with the decay and minus the CP conjugated. For this to be non-zero, right? We need that this phases, this is strong phases, and the weak phases have to be different. Otherwise, they're zero, and otherwise you have ACP zero, meaning that you don't have CP violation, right? So the weak phase is CKM. That's the only source we have so far, and but the strong phase, it's QCD, and then the traditional way of thinking is that the penguin diagram plus the tree diagrams will give you the strong and weak phases that you need. But so far, this is not enough. So this was proposed by Bender, Silverstone, and Sony. It's very famous, and it's known as BSS model. It's normally the way we teach the students on the classroom, saying, oh, we can have CP violation when we have this. But the problem is that this is definitely not enough. The numbers that we obtain by using these calculations are definitely not enough. So we need more. And what is more? More is the hadronic interactions. This is non-perturbative contribution from hadrons interactions, and then they can interact in all sorts of waves like rescatterings, changing resonance, etc. And then, of course, those resonance, they will lead like some signatures on Ballard's plot. So we cannot ignore these hadronic interactions. Great. So how this fulfill in our data, in our understanding of CP violation on this data? And so if we analyzing more carefully the Dalitz plot, this Dalitz plots here, we see that it seems to have a dynamic effect between like same regions of the phase space that have like opposite CP violation. So being more specific, we need to recall for CPT theorem. So what CPT tells us? CPT tells us that the particle lifetime have to be the same as the antiparticle lifetime. So if we consider like that one channel of this particle have a positive CP violation, we need another channel with a negative to, in the end up to zero. And this seems to suggest that there is a connection between different channels in the same decay. And we can see this more clearly, like looking to the projections. So this is our projections of those data, and the white ones, I don't know if you can see here, here are the B minus, so are the particle ones, and then the black dot, the black triangles are the B plus. And then we can see, for instance, K pi pi, we have more B minus than B plus in this region between 1 and 1.5, where in here in 3 kaons, in the same region, we have more B plus than B minus. So it seems to be a correlation between those channels that can talk to each other towards final state interaction. So we know that pi pi is strongly coupled to KK. So what Tobias and Inácio suggested back in 14 was that we can understand this process if we describe that the one that is carrying this signal or this CP violation is the rescattering between pi pi and KK. And this was a very striking idea, and this was used and implemented in LHCb data in different amplitudes. And recently, with José Peláez, we revisit this main work, and we improve the final state interaction amplitudes. So we put better pi pi to KK amplitudes, and also we include pi pi to pi pi dispersive analysis. And then, so this was what was the results before. You can see that the errors bar are quite big. And then by using like something better between this region 1 and 1.5, we have a better descriptions, but the main idea is that the main conclusions remain the same. So the dominant amplitude here is the pi pi to KK, and then can explain and can accommodate the CP violation in this region. So we also use the same idea on the high energy physics in the high energy mass region. So we see that the Dalitz plot also have like CP violations. They are, so we're discussing before, very on the corner of the phase space, but there's small CP violation also on the high mass region. And so we propose a similar effects between pions and kaons, but now with the intermediate DD bar interaction. So BB bar, DD bar can go to pi pi and then can go to KK. And this can happen towards this triangle diagram here. And of course, you can think about, but this suppress it, right? Because this is a triangle and then have a kinematic suppression. But the point is that this weak vertex here, it's 1,000 times bigger than the branching fractions of producing directly hadrons themselves. So even if this is suppressed, we can think about like this being sizable contributions to the final states. Great. So this I'm showing this more briefly, not going to the details of this. Oops, but just to say that with this mechanism, we understand that this is data and this is our phase. So we can have a changing sign in the phase, and this will allow us to describe this changing in sign on the CP violation as well. So we also use this on B to 3 pions, and we select only the like above 3 GeV, because then we don't have to deal with the low energy resonances. So let's only look at the high energy. And then by doing that, we obtain this toy. So this is 3 GeV. This is this part of the data. And as we can see here, it's a very simple model, very, very simple, only considering that we have a triangle plus a constant and the weak phase, which will mimic the tree level diagram. We can reproduce this signature at the high mass. And then when we look to the data, of course, there's a lot of things missing, but it's an important mechanism. And we can somehow mimic this pattern at high mass. And now we want to test this on data. Because the one is here, so just the one to be convinced. Great. So, okay. So, and then charm. So we have all this experience on the bit physics, and then we thought about like, okay, why this is not, if it's present on the biphysics, it should be there on the charm sector as well. And so we said, well, look into this final states. It's very tempting to think that the pi and kk are not like talking to each other. So it seems obvious for us that this has to be playing something here as well. And but what happened to these decays? They are single Cabib suppressed decays. So the weak phase on the D on pi, so D0 to pi is lambda 5. So it's very, very tiny. We kind of expect that, right? The CP violation on charm. That's why it took so long for them to be observed. And but on the kaon sector, this is even smaller. So it's 20 times smaller on D0 to kk than D0 to pi. So we kind of neglect the phase here, and considering that the weak phase is only present on D0 to pi. So just to mention that yeah, and of course the strong phase we will not consider in the penguin, and we will consider in the hadronic final state interactions. But just to mention that there's a long list of people working on this. Like this is really like something hardly being discussed now. So there is a strong debate. It took us a year to publish a paper because we were in this fight about making a point. So and what is our point? So it's basically that we can have two paths. We can have D0 going directly to kk, but we can also have D0 interacting to pi and then going to kk. And then we know this phase, right? We know this phase experimentally. We know this phase since the 80s from Monique data and so all these things. And so we decided to build the amplitudes imposing 3 constraints. So the CPT, meaning that the only channels that are taking place here are pi and kk. This is an assumption, right? I mean, we know that's not 100% sure, but we are assuming that they are the main channels interacting here. And we also will call for Watson theorem to use those strong phases directly from data without needing to calculate pi to kk or pi like to choose a model. And we impose the unitarity of the strong matrix. So a very like simple and important claims that we use to build our amplitude, and that's it. So that's everything we need. So we dress, instead of calculating the penguins, we simply dress the 3-level diagrams with the final state interactions. So for instance, D0 to kk, this is a 3-level, and then we dress it with kk to kk, but also this could have been like a 3 pi final states, where we then dress it with pi to kk final states. So we just did that, and we can do, of course, the same for D0 to pi, and then we have similar amplitudes here, but the overall amplitude is different. And so if you carefully look for our amplitudes, we only have CKM elements, this eta and delta phases that they are from the S matrix of pi to kk or pi to pi, etc. And A0, so the things that we don't know is this quantity, the intensity of this amplitude, because of course we are not calculating these diagrams from first principles, so we don't know exactly this weak structure amplitude, but we are assuming that they are real, right? So this is the other assumption. And then from Watson theorem, as I said, we can use this information here from data, and we can extract the quantities that we need. So for instance, on pi to kk, we use the data is like magnitude and phase, and then we use this just the Pelaez in Hölder's parameterization to extract the inelasticity in pi to kk, which is eta 0.973. Okay, so we can just build the amplitude. This is just math, so not going to the details of this. We need the delta gamma, which is just square this amplitude, do the math, and then you impose CPT, and then you have this function here, which we need somehow to quantify this little a and little akk and little a pi, and then we can do that by using the branching fractions information from this decay. So we did that, and this is our results. I want to let more time for discussion. So just mentioning that we know how to calculate that, and we can obtain the individual ACPs here as a function of inelasticity. And why I left in function of inelasticity? Because as you saw from the data before, there is a huge uncertainty on this inelasticities on data. So it's not very clear which inelasticity to pick. So we decided to leave our results and then see which inelasticity. So we took two. So one is the one directly from pi kk data that I showed you before. And this from the delta CP, if we compare to LHCb data, we have like 3 sigma deviation from the results. But this is so far the largest theoretical prediction we have so far in the literature. But we don't like it because we don't like these eta. So the way to extract this is not, I mean, the systematic uncertainties are unknown. So it's not very clear how we because we extract this indirectly. So if we use on the other side an eta directly from pi to pi, which is also not 100% true from the theoretical point of view, because we are saying that all the inelasticity in pi to pi go to kk. We have this eta 0.78, and then the approximation we did to calculate the little a's are not valid anymore, but we can do it numerically, and then this is the results we obtain, which is now 1 sigma. So of course we know that this is like too much, but also we don't like this. So we believe we have boundaries, the lower and the high boundary of this ACP, but data is definitely on the middle. So I think this is very, very important and very striking results. So with this, we can, of course, compare the individual ACP as well. And we arrive to these results. And although we are 2 sigma away, there's a very important difference on the sign of this ACP for kk, which of course is compatible with 0 here. But we are very sure on the theoretical point of view that this sign has to be negative. So if this data, of course, we need more data, but if the data confirm and then reach the ACP here, and then we have to revisit our model that, okay, we can't be, there's small things to be considered. But so far, we are pretty satisfied with these results. And of course, when we go to 3-body physics, this is what we want to do next. We also expect these effects to be present there, but now instead of a point, we need to consider a full distribution of amplitudes here. And this is what we've been working now. So stay tuned. And so just to final remarks, I show you different examples and different studies we've been doing in the last 10 years, where the strong fine state interaction between the hadrons are crucial and needed to understand the CP violation on this process. And yeah, so thanks a lot.
Questions?
I have one question on your remark that pi and kk don't talk to each other. But if we look at the F0980, meson, then we know that there is talking to each
No,
other.
they are talking. I said no talking. No, they're
Yeah,
talking.
yeah. Well, in first order. But how does the structure of such resonances enter your scheme?
So that's a very good question. So they're here. I mean, if you look for the if you look for this data here, so this is pi to kk. So F0 is here because look, the phase space started one. So F0 is sitting on the threshold of kk. And it's enhanced by this threshold. So you have a resonance sitting on a threshold. So it's boom, it's a super peak. If you see like on the, then I have to go back to the pi data. It's also, oops, it's also here, right? This big jump here is exactly on the threshold. And so it's a resonance sitting there. So it's here. We are not doing a model that specify the dynamic of the interaction. Why? Because we are only interested in a CP violation in one point, because we're talking about two-body decays. The energy of the center of mass is fixed. So we are talking about something that is happening here in 1.84, 1.84 GeV, which is the mass of MD0. So we are taking data points from here. We are not, but when we do three-body physics, then we're going to have a distribution. Then we have to take about, we will be more careful about the dynamics of things in the amplitude. So,
more questions to Patricia? Okay, so thank you, Patricia, for the now we have Giorgio Torrieri. Oh, Giorgio, please. Okay. So now Giorgio will talk about hydrodynamics with 50 particles. Yeah. Okay, please, Giorgio.
Okay.
Go ahead.
Thank you so much for inviting me to this great city and give me an opportunity to speak, especially because I will talk about something which is not, you would think it's not directly related to this conference, but I'm going to show you it is, especially if you sort of have the patience to get until the last slide when I will try to make a direct correction. It's still in development. It's written. It's based on these papers there. The referee report for this one came out yesterday that basically says they don't understand what I'm talking about. So I'm hoping that I'll do better here. Okay, so I come from heavy ion physics, and as you probably do know, and you might be skeptical about, it has been defined by this: we found the perfect liquid in heavy ion collisions. I mean, there was like all kinds of press a few years ago, and there was even a coffee mug, which I used to have and I lost. And the science of it was based on these azimuthal correlations. The science of it was based on these azimuthal correlations, which essentially were shown to be not just trivial things like momentum conservation, because it's correlations of very many particles, but which actually follow pressure gradients quite closely. And if you try to fit them to a hydrodynamic code, basically ideal hydrodynamics fits really well. And if you put in even a very small viscosity, the data and the hydrodynamic model goes away. So this is basically the motivation for this perfect fluid idea. And it led to a lot of theoretical development. Relativistic hydrodynamics would sort of develop between the 50s and the 70s, and then it went into a hiatus because who cares about relativistic fluids? And it turns out that nuclear physicists might have to, and there was really some very high quality work. And the basic summary is that hydrodynamics can be thought of as an effective theory where we separate the energy momentum tensor and any conserved quantity tensor, but you have a energy momentum tensor, and then you have a whole bunch of conserved vector currents, rank 1 vector currents, and you separate them into an equilibrium and an equilibrium part, and then you can basically use Kubo relations. I mean, the fluctuation dissipation theorem in the infrared asymptotic limit to calculate things like the viscosity from correlators. That's wonderful. What's the problem with this? Two problems. The first one is that it's a classical theory. So if you do use fluctuations to calculate things like viscosity, but you don't use fluctuations as sort of probabilistic things. Then you sort of put the viscosity into gradients and the system still evolves as a deterministic system. And considering, and the other thing is that you kind of lose flavor of universality. It turns out that you need to know a lot about microscopic theories, which in our field basically reduce themselves to models like the Boltzmann equation and string theory related models, which was part of the reason why this perfect fluid stuff became so famous, because we experimentally confirmed string theory because the lowest viscosity that was found could be calculated from a string theory model. Fine. The problem is that once you switch on the LHC and you look at higher multiplicity, very small events, it turns out that exactly the same hydrodynamic signals and exactly the same collectivity are found in events with basically 20 particles. And in fact, in a particular definition, which I really like, where you basically look at cumulants, and the LHC has high luminosity enough that you can measure, it's an experimental measurement. You can measure high-level cumulants in small systems. It actually turns out that systems with like 30 particles are just as collective as systems with 3,000 particles, like AA collisions. And from the point of view of this effective theory based on gradients where everything is deterministic, this is at least weird. Because even if viscosity is 0, forget string theory, let's just do 0 viscosity. At equilibrium, you have fluctuations. I mean, statistical mechanics doesn't say the state with most microstates is certain. It says all microstates are equally likely. And in the thermodynamic limit, the state with most microstates really becomes certain. But 20 particles is not the thermodynamic limit. So this is really strange. And the bottom line, I know that in another subject, there are people skeptical of hydrodynamics. And, you know, this is, to me, either we are radically misunderstanding the data, which honestly is a possibility, but no one found a better description, so why not? Or we need to really understand the role of fluctuations in hydrodynamics well. And for this, we need to derive hydrodynamics a different way, not the way that it was derived using Kubo formulas and the asymptotic limit of transport theory. And this might actually be related to everyday physics. If you can look up the Brazil nut effect on Wikipedia, basically, if you have a jar of nuts and basically systems, it does seem from other areas of physics that hydrodynamics arises in very small systems, in systems with very few degrees of freedom. The reason why the Brazil nut for the Portuguese speakers, the castanha de Pará, is on top of the jar of nuts you keep in the kitchen is basically, it turns out to be something like Archimedes' principle. But the reason why hydrodynamics would work in something like a jar of nuts, you'd be surprised to know, is still not understood. There are people publishing PRLs about it. The bottom line is strongly correlated systems subject to random fluctuations can look very hydrodynamical without an underlying theory, and no one really knows why that works. Going back to sort of more particle physics from nuts. Actually, statistical mechanics, statistical mechanics has been known to model particle collisions for quite a long time. And moreover, this doesn't surprise people too much, and you have relatively trivial explanations for it, such as phase space dominates. I mean, Fermi wrote about it in the 50s, that maybe Fermi's golden rule achieves a limit where all matrix elements are equal, and then phase space basically dominates, and that's not too different from microstates in statistical mechanics. Well, and in fact, there are slightly less arms-waving arguments about it from quantum mechanics. And there is something called the Berry conjecture, the Bohigas conjecture, the eigenstate thermalization hypothesis, canonical typicality, and so on and so forth, which basically says that if a system is classically chaotic and you quantize it and you look at the high-lying energy levels much above the ground state, the density matrix looks effectively like a random matrix. So these quantum systems don't need to equilibrate, they're born in equilibrium. That is a concept which outside of particle physics has never really been shown to work in field theory, but outside of particle physics is pretty popular. What people do not know is what happens if you assume this to be true, but you only assume this to be true in a cell, and then you look at how cells look at each other. This problem has never really been looked at. And the question is, how many cells and how many particles per cell, and what is the role of fluctuations if you do have a strongly coupled system? Its density matrix of coarse grain to every cell looks random, but just by causality, neighboring cells cannot instantly thermalize, and neighboring cells have different energy and momentum. And what is an evolution of a system like that? Well, as it turns out, there is another very elegant way to look at thermodynamics, to look at hydrodynamics, which could help, amazingly enough. Not at first sight it could help, but I hope to convince you that it helps. People like Jacques and Alberto Nicolis and Dan Thompson and collaborators have noticed that Lagrangian hydrodynamics can be described, Lagrangian ideal hydrodynamics without viscosity, forget viscosity. Lagrangian ideal hydrodynamics can be described as a field theory with local symmetries. So what is Lagrangian hydrodynamics? Eulerian hydrodynamics is when you look at the energy momentum tensor. Lagrangian hydrodynamics is when you look at every cell. You're co-moving with a cell, and you're looking you're sitting on a cell and you're looking at how it moves. How long do I have? How long do I have? Okay, 15 minutes, perfect, wonderful. Yeah, and it turns out, what does it mean that you're sitting on a cell? It means that on that cell, you have a bunch of Cartesian coordinates there. How do you put your Cartesian coordinates? Well, here is the point. There is many ways, and you can even twist the coordinates from one moment of time to the next and from one cell to the next, and your description will be the same. Because as you learned in elementary school, a cell is locally thermalized and pressure in every cell comes from every direction. And that's sort of the point. And it actually turns out that this can be put in a mathematically very nice way, in which basically hydrodynamics is uniquely defined as a theory of volume preserving diffeomorphisms in SO3. Relativistic hydrodynamics is the theory of volume preserving diffeomorphisms in SO3. You have homogeneity and isotropy. Homogeneity and isotropy, basically you can rotate the cell as you want, and that's a redundancy. That's a gauge-like symmetry. But then you can also compress and twist every volume cell as long as its volume is invariant. And that's a global, it's an infinite dimensional global symmetry that relates one system to the next. And this is very similar to GR. Basically, it's instead of local Lorentz invariance, it becomes local SO3 invariance with volume preserving. For people who know sort of physics beyond GR, this is what's called unimodal gravity. And also the Lagrangian, there is no curvature in hydrodynamics. The Lagrangian is the cosmological constant, which in plain English means if you leave a lump of fluid in the vacuum, it will just expand, and the expansion will look very similar to Hubble expansion. We all know that. For people who know differential geometry, it's very easy to see that an arbitrary Lagrangian, written in terms of the determinant, written in terms of the Jacobian of your Lagrangian coordinates, its energy momentum tensor looks exactly like the energy momentum of ideal fluids. I mean, we all know this. And you also have a killing vector, which we identify with the flow. There is exactly one vector which is always perpendicular to all the allowed coordinate systems. And this vector is, of course, the killing vector, and it's the flow. If you add a chemical potential, we all know that a vector conserved current is the Noether current of a phase invariance. And you can make sure that this current is strictly proportional to the entropy current if you do a gauge-like diffeomorphism invariance where the phase can be a function, an arbitrary function of the Lagrangian coordinates. If you do this, because of the fact that flow is identified with a killing vector, the conserved current will always be very similar to will always be proportional to the gauge current. And you can expand around the thermal background, and you will have sound waves are sort of compressibility waves, vortices are sort of rotational waves, and you can derive everything you know about hydrodynamics this way. You can also derive that it's sort of unstable about fluctuations in the way that I will talk about. But the question is, I mean, this is very elegant. But what is the connection with the statistical mechanics that we know and love from heavy ion physics, that everything is thermalized in every cell? Is there a connection to it? And surprisingly enough, there is. Because it turns out that is related to the concept of ergodicity. So if you look back to statistical mechanics, if you look back to your undergraduate statistical mechanics lectures, there was always a very hand-waving lecture that talked about chaos and phase space and Poincare recurrence relations and systems being ergodic. And then came the microcanonical ensemble and so on and so forth. An ergodic system is a system where the time evolution is equivalent to the evolution under the ensemble of microstates, It's very non-trivial to show that a certain system is ergodic, and certainly most classical systems are, and how this is related to the real world is something that is sort of in research. But basically all of statistical mechanics comes from this concept, comes from the fact that we can approximate sort of chaotic many-particle systems as being ergodic. Ergodicity is also not a Lorentz invariant concept, obviously, because on the one side you have time evolution, on the other side you have evolution over the space of microstates where time is absent, sort of a configuration in phase space. So it's not a concept which has anything to do with Lorentz invariance. Can we make it slightly more Lorentz invariance, considering that, as I said, hydrodynamics is sort of thermodynamics in every cell? So can we use this local ergodicity issue, make it slightly more Lorentz invariant? And we have to do this because, of course, we're talking about relativistic hydrodynamics. And in relativity, thank you. And in relativity, time is frame dependent. Well, I have 5 minutes, so I'll quickly talk about the concept. You can read the paper for details. The point is that instead of time, we can think about a foliation. Sort of everywhere in space, we have this, we put in a time-like vector and we move it forward. And then we ask, can something be ergodic in every foliation? Obviously, it cannot, because eventually time will stop, like in the infinite momentum frame defined in Light-Cone physics, just to anticipate where I'm going. However, we can have a family of foliations which are sort of smooth with respect to each other. And we can ask ourselves, what kind of symmetry do we need for something to look ergodic in a smooth family of foliations? And then we can use elementary differential geometry and what we know about delta functions to convince ourselves, because of the fact that every conserved current, so ergodicity basically means that everything allowed by conserved currents is equally probable. We can use Noether's theorem to rewrite conserved currents as sort of symmetries as deformations of the Lagrangian. We can use the fact that a foliation is a foliation. Oh, sorry, I'm going the wrong way. We can use the fact that a foliation is always a Lorentz boost and a rescaling, and the Lorentz boost has determinant 1. A Lorentz boost has determinant 1, so the important thing is rescaling, and we can basically say, well, if ergodicity is the same in every foliation, we can have an equation where we take out time evolution, and we will have an equation in terms of delta functions and Lagrangians. And if we solve it, we get this, to me, amazing result that for the system to be regarded as ergodic in every foliation, it will have exactly the symmetries of Lagrangian hydrodynamics, volume-preserving diffeomorphism boosts. So yes, there is a connection between the two pictures. The connection between the two pictures is ergodicity in every relativistic foliation. QED, wonderful. That's nice, that's elegant. What can we do with this? Well, the point is, something being approximately ergodic and something having many degrees of freedom are very different statements, and they don't necessarily commute. So this idea that the system is ergodic in every foliation could be true even if the system has comparatively few degrees of freedom per cell. And this is the connection with hydrodynamics and small systems. And this becomes very important if you look at the eigenstate thermalization hypothesis again. Because in eigenstate thermalization hypothesis, we can think of statistical mechanics as ergodicity as the fact that the density matrix is random. And now you ask, well, what is random? And this really seems to work very well in quantum systems, where systems don't become thermalized. They sort of start as being thermalized, because the solution to the Schrodinger equation, the density matrix, really looks like a density matrix. And this has been looked at like in numerical simulations and such. Here's in nature. Again, not in quantum field theory. There are recent efforts to extend this to quantum field theory. And the point here is that the proof goes because of the fact that rotations and volume preserving diffeomorphisms become unitary matrices, the proof transfers from classical mechanics to quantum mechanics really well. So if every coarse-grained density matrix in every cell looks random, the system will acquire the symmetries of statistical mechanics. And this gives you a conjecture that, after all, you don't need an infinite number of particles if the system is quantum and strongly coupled in every cell. Perhaps you don't need an infinite number of particles in every cell to exhibit ideal hydrodynamic behavior. Which brings me to the reason of why am I talking about this in a meeting called Light-Cone. There was also, I mean, this is sort of the paper that started the subject, Karzev, and he was wondering about the proton and the nucleus are sort of zero entropy ground states. What does this have to do with how come a hadronic collision has entropy? And his sort of heuristic explanation is that in the infinite momentum limit, the partons go through each other. They're sort of spread around in Bjork and X, and we are looking at slices of Bjork and X, and this essentially decorrelates the system and makes what was initially a ground state instantaneously into a set of maximally random, maximally incoherent states, which looks like the microcanonical ensemble. So the question is, what happens to the diffeomorphisms that I was volume-preserving diffeomorphisms I was talking about in the Light-Cone picture, and could this picture be adapted to the parton information, to information in parton rapidity range? Well, I kind of have no idea. I did the proof for hydrodynamics, but perhaps there are people who are interested in this, and this is something that I'm planning to look at sort of next. thank you very much. This is a good place to stop. Thank you.
Questions to Giorgio?
So thank you, Giorgio, for a very nice talk. So I have a very simple question related to the beginning of the talk. So how do you, no, it's not necessary to go there, I think. But how would you connect all this new picture to the usual expansion in gradients of hydrodynamics?
Very, very good question. I've been arguing about this for the Kubo formula, basically. Both the Kubo formula and, for example, Schwinger-Keldysh field theory hide an assumption in it, which is the k going to zero limit. The k going to zero limit basically says, I mean, this comes from fluctuation dissipation. So you're like, what do you mean? You are including fluctuations. Yes, you are including fluctuations, but you're also assuming that the typical fluctuation mode is much, much smaller in configuration space than the gradient. So basically, fluctuations and gradients don't talk to each other. So in hydrodynamics in small systems, that of course becomes unreliable. Because basically, Kubo formula assumes the thermodynamic limit. But statistical mechanics is not the thermodynamic limit. The thermodynamic limit is a limit of statistical mechanics.
More questions to Giorgio? I have a question. Giorgio, you mentioned this entanglement. You are saying that degrees of freedom that are inside our, I mean, the nucleons or this many body system that you have, they are entangled due to the interaction. How do you, can you relate that to the structure of the nucleon itself that we heard there are plenty of gluons? And can you mention something?
Yeah, it's a very good question. There is actually, there is a very good introduction that Karzev wrote. It's not this paper. He wrote a paper for the Royal Society. If you Google Karzev and Royal Society, you'll find it. You can basically prove QCD factorization from quantum information theory, from density matrices, because the whole point is that every parton lives in a Bjorken X. And when you are observing hadrons, you're sort of, there is a map because of asymptotic freedom from Bjorken X to from different slices of Bjorken X. They talk to each other, and it's much more likely that things within a similar Bjorken X talk to each other. And you're basically observing a subsystem of a very large system. So you have to coarse grain the density matrix this way. And you can prove approximately QCD factorization basically from this. With some non-trivial consequences. For example, the spin structure doesn't factorize this way. But if you also coarse grain over spin, you factorize this way. So the idea, if you want, is that when you are, even if you have sort of a 4-pi detector, if you're observing single hadrons, you're observing over a range of X. Every hadron comes from an independent X source, and there is no way to look at which hadron came from which X source exactly. So you have something that looks like a thermalized system. So arms waving explanation. Yeah.
More questions to Giorgio? Okay.
Hi, Giorgio. This is follow-on question about this. We know rapidity evolution equations in QCD. There are a bunch of them: G-walk, BK, BFK.
Sure.
You know, I suggest that, say, GWOC could be reformulated as a hydro evolution. And what would be the role, say, of viscosity there? Do you have viscosity there or anything like that? This is a sentence, which is what I am reading.
Yeah, perhaps. I don't know. I mean, from what I'm not an expert. I'm not an expert. There is one of the letters is here. Yeah. From what I understood, it's more like a nonlinear diffusion equation, isn't it? Than a hydro equation. But these are related concepts. I mean, what I mean by hydro is that you have this decorrelation. You have this decorrelation that I was talking about, and then in the next time step, you have another total decorrelation, and then in the next time step, you have another decorrelation, and then in the next time step, you have another decorrelation. I think that's not quite what happens in nonlinear QCD. But I'm really not an expert, so I'm scared of saying something stupid. Yeah.
So, I mean, there will time in the coffee break to discuss more. So I would like to thank you, all the speakers, Giorgio, for this moment. The coffee break is in the same place we have the registration. Up to 11. Wayne Polizo will talk about light front puzzles. Please, Wayne. You have that, yeah.
My first time in Brazil, basically did a little tour yesterday and just found the whole place very breathtaking. So it's been a really great experience for me. What I want to talk about is something I call light front puzzles. There are a lot of confusing things about light front quantum field theory and trying to contrast it with canonical.
Yeah.
Oh, okay.
Yeah.
This one here.
Oh,
Yeah, you can use this one as well.
Okay.
Wayne,
Either one.
if you prefer this one.
oh, no, I'll use this one. This is
Okay,
fine.
perfect.
Okay. Okay, anyway, what I want to talk about is something I'm calling light front puzzles. And these are just things, at least in my way of trying to understand them, is how I try to resolve some of the differences between light front quantum field theory and canonical or covariant quantum field theory. Let me just start by let's see this way. Okay, just first, just to review some of the reasons why we're doing light front quantum field theory. One is that it has a Hamiltonian form, which means basically you can do non-perturbative calculations and they're reduced to linear algebra, which is one of the advantages of it. Second thing is when you're dealing with weak and electromagnetic probes, you start with something in one frame, you hit it and it moves to another frame. So you've got to be able to basically boost your hadronic states. And the nice thing about light front is that the boosts are all kinematic. So basically, if you have a model wave function, you can still rigorously boost it to a different frame. Another thing about the light front boosts is they actually form a closed subgroup, which means that there's no Wigner rotations, which makes it nice. And also, for the same reason, you get frame independent impulse approximations. The other thing that's very nice is the vacuum is essentially trivial. And I'll talk about that a little bit. And finally, the fields, when you restrict them to a light front, they're irreducible, which means basically you can build any operator or any state using fields restricted to the light front. And lastly, if you understand Dirac's formulations of Hamiltonian quantum mechanics, the light front has the largest kinematic subgroup, which means the largest number of generators that basically have no interactions. And those include 3 boosts, 3 translations along the plane tangent to the light cone, and 1 rotation about, if you want to call it, the z-axis. Okay. Now, the puzzles I want to talk about is the first one that got me interested in this was what I call the problem of inequivalent representations of the canonical commutation relations. And there's something called the Stone-von Neumann theorem, which basically says if you have P's and Q's that satisfy canonical commutation relations, they're going to be related by unitary transformation. And when you go to infinite number of degrees of freedom, that theorem breaks down. And even for free fields with different masses, it breaks down. And on the other hand, in the light front case, the vacua all seem to be the same. And that's puzzled me for a while. Also on the light front, there's the problem of an ill-posed initial value problem. The light front has some points that are they're causally connected. And the question is, can you actually formulate an initial value problem properly on that? There's a problem of rotational covariance, and I'll talk about what I mean by that. But it turns out if you look at the P minus and the kinematic subgroup, that doesn't generate the whole algebra. So basically, rotational invariance and also space reflection invariance are something you have to put in by hand, sort of. And that's related to the problem of zero modes. And then finally, the problem of spontaneously broken symmetries. If you try to calculate the charge operator that comes from spontaneously broken symmetries, it doesn't couple to a Goldstone boson. And so those are the puzzles. And I'm going to basically try and give you my interpretation of what's going on here. You may or may not agree with it, but let me just kind of give you a brief summary of what I'll conclude in case I don't finish. And first of all, each theory has one true dynamical vacuum. Okay, and that's something that everybody suspects. On the other hand, if you look at the Whiteman functions, which are vacuum expectation values of the Heisenberg fields, or polynomials in them, it turns out that you can actually write those as vacuum expectation values of operators restricted to the light front. And when you do that, you can use the vacuum of any theory. So basically, you can use any trivial vacuum to calculate those. And I'll explain exactly how that comes about.
And the dynamical content of different theories is not contained in the vacuum so much, at least on the light front. It's contained in some subalgebra of operators on the light front, and I'll explain that in some detail. Rotational invariance and space reflection, they're not included in the dynamics at all, in P minus in the kinematic generators, and I'll talk about that. And finally, the spontaneously symmetry breaking charges on the light front, they have no dynamical content, but you can get to something that couples to Goldstone boson using the irreducibility of the algebra. So those are, basically a shorthand thing of what I'm going to try to explain, and I'll try and clarify all these marks in the next couple of slides here. So the first thing, I think about these in terms of algebras of operators, and there's three basic algebras. The first one I'll call the Heisenberg algebra. Is this separate thing? Maybe not. Oops, wrong way. Okay, and that's basically you take fields in 4 dimensions and you smear them with 4-dimensional test functions. The next one is the canonical algebra, where you have basically fields that satisfy canonical commutation relations of pi and a phi, and those you smear against 3-dimensional test functions. And then finally, you take a field restricted to the light front, and here you smear them with functions on the light front that vanish at p plus equal to 0. And each of these basically is what I call an irreducible algebra. You can pretty much build anything out of them. And they're different algebras though. Okay. And as far as vacuum states are, I think of those as basically linear functionals on these algebras. So if I have a state psi that's given by some polynomial applied to the vacuum, if I take an inner product, there's a vacuum expectation value of A dag and B. And that's a linear functional on products of fields. Those linear functionals can be basically characterized by essentially vacuum expectation values in this Heisenberg vacuum in terms of polynomials of products of field, or just essentially, if you know the vacuum expectation value of all products of fields, smeared fields, those are the Whiteman distributions. You can build the theory back up. Okay. In the canonical case, you have pi's and phi's, and you can extract, if you want, an annihilation operator from those, and you can define your vacuum alternatively in terms of the annihilation operator applied to the canonical vacuum, or again, the vacuum expectation values of products of canonical fields. Okay. And the light front, similar thing. If you have a field restricted to the light front, you can extract the creation and annihilation operators just from the field on the light front. You can define a light front vacuum that basically annihilation annihilates the light front vacuum. But it turns out that thing doesn't really have enough information to uniquely determine the Heisenberg vacuum, the one that either one of these two vacuums that's up here. I'm not sure how I do the pointer here, but the way to do it is just separate. Or... you just hold that down. Okay. Okay, good. Thank you. All right. And then finally, there's one more concept that's important here, and that's irreducibility. If I basically have an A and an A dagger, and I have any operator that can use with all the A's and all the A daggers for all possible A's and A daggers, then basically that has to be proportional to the identity. And in the canonical case, you can basically extract the A's and A daggers from the fields, the pi's, the phi's and the pi's. The light front case, you can extract it from fields on the light front. Okay, both of these guys. These two guys are related by this simple relationship everybody knows for the free fields. And you'll notice the red things are there because they involve the mass, which is the dynamics. Okay. Okay, so now I want to talk about free fields, and there's two things that are really central to this. First, I have my Heisenberg fields. These are just the ordinary fields you get from textbooks, and you can write those in terms of creation and annihilation. But what I just showed on the left side is the creation and annihilation operators can be expressed in terms of either the canonical equal time fields or fields on the light front. And if you put these two concepts together, you trivially get that you can write the Heisenberg fields directly in terms of fields on the light front, or basically canonical fields for some fixed time. It looks like, and what this is saying is that the Heisenberg fields here can be expressed in terms of some linear combination of the two canonical fields, where there's basically this function here that's a fixed time function, basically involves some kernel you have to integrate against the four-dimensional test function. Life-front case, similar thing happens. Basically, you have some function that comes from the four-dimensional test function. Integrate that against fields on the light front. These y tildes basically means coordinates on the light front. And the bottom line is there's a kernel, just like there was before. What this kernel looks like is essentially, it just puts the mass shell condition. So I'm just looking deep about this. Okay. And the interesting thing about this is like basically I'm doing evolution off of the light front. That's basically derivatives with respect to x plus. When you push it through this k operator, basically you get the light front Hamiltonian. Which is very nice. Okay, so that's for free field. A similar thing happens with interacting fields. You've got to make some assumptions, namely that the field satisfies some axioms, and that basically the fields you get are asymptotically complete, which means that's unitary. Or another way of saying it, basically have in fields and out fields, and basically each one separately be used to build up the whole filter space. Now, the nice thing about in fields or out fields is that basically, if you calculate vacuum expectation values with the full Heisenberg vacuum, they're the same as vacuum expectation values, free fields and physical mass. And so they're unitarily related to basically free field. And because of that, I can do this trick where I basically take my in field and I can basically use this kernel and basically express it in terms of fields on the light front. So basically I can express basically smeared in fields with in terms of basically fields on the light front. And in this case, because these fields are also irreducible, I can basically expand the Heisenberg fields in terms of the in field. And there's an old paper, it's one of the old sort of L and Z papers, it's really by Glasser and Zimmerman. And basically we give a formula for actually expanding the Heisenberg field in terms of normal products of in fields. These end up being retarded commutator functions involving the Heisenberg field products of in fields. You combine these results together, then basically you find out that your Heisenberg field for an interacting theory can be expressed in terms of some smearing function. That's your Heisenberg smearing function with these kernels here, and then you basically have these operators that put all these light front things on the mass shell, and then everything what you have left is just a product of light front fields. So basically, if you want, you can basically express Heisenberg fields in terms of some very complicated dynamical subalgebra of free fields on the light. Okay, so these subalgebras are the important for either this one, or if I go back to the slide to the one I got by basically smearing more essentially the algebra I get by basically smearing my light front fields with these kinds of functions here. That's not the whole. Okay, so what this tells you basically is that you can write all the fields in terms of fields on the light front. And the important thing is once you get on the light front, all the vacuum things are all the same. So you can use any vacuum you want to calculate these expectations. So in particular, if you want, you can calculate all the light functions of the interacting in principle, basically in terms of fields on the light front using any vacuum you want. So in that sense, even though there's a true physical vacuum for doing calculations of the light front, you can use anyone else. The caveat is there's some renormalization involved. It's highly non-trivial that you get to the light front. But let me just explain what's going on here. If I basically look at some algebra of field operators in the Heisenberg algebra, these guys here, I can basically go through this conversion process and I get the subalgebra of fields on the light front. And I can use the correct light front vacuum there, but I can change to a different light front vacuum. And as long as I have the same algebra, it doesn't matter. On the other hand, if I change my Heisenberg vacuum using the same algebra, I'll get something that's inequivalently different. And if I basically use the correct light front algebra, light front vacuum with different algebras, I get something inequivalent even when I use the same vacuum field. So anyway, point is the vacuum expectation of the smeared Heisenberg fields can be expressed as light current vacuum expectation subalgebra, and I can use any light current vacuum I want to calculate this vacuum expectation. So let me now come to my puzzles here. And the first one is this notion of inequivalent representation. Just to remind you what this is. It goes back to a fairly old papers in Stonewall. But if you have basically two sets of P's and Q's that basically satisfy canonical permutation relations, you think about two harmonic oscillators. You can measure P's and Q's in terms of creation and annihilation operators. It's a natural oscillator frequency that comes here. And basically the A's and A daggers are related by mixed-states and linear canonical transformation. Hyperbolic cosine of parameter eta involves basically ratios of two frequencies. And it turns out these are related by a linear transformation, the generator, given by this expression here in terms of A's and A daggers. And the problem is when you have an infinite number of degrees of freedom, basically the generator of this unitary transformation basically takes you out of any vector in the Hilbert space gets mapped to something. And this is the problem with the Stone-von theorem. I mean, the whole point of Stone-von was to show that Heisenberg and Schrodinger representations of quantum mechanics were the same. But when you go to infinite numbers of degrees of freedom, what ends up happening if you do this with fields, all of a sudden these A's and A daggers depend on this continuous parameter P. These hyperbolic cosines also depend on P parameters with different masses. So this is two free fields with different masses. And it turns out if you look at just what this generator does to the vacuum, basically it gives you some expression that involves the square of this eta that goes with this, and then it's a delta zero, and this thing blows back. Basically, when you have free fields with different masses, they live in completely inequivalent anyway, in terms of how you resolve this, the point is that in the light front case, if you go to these subalgebras that have the mass tagged in there, the dynamics tagged in, those subalgebras give you something that's inequivalent, even though the full light algebra, which is something that's trivial inequivalence. So this is my way of trying to understand this notion of equivalent inequivalence. The point is there's no dynamics in the full light front algebra. It's only when you restrict this algebra. The triviality of the vacuum, this is something everybody, I think, in the field knows, but just to remind you, if I look at P plus has to be the translation operator annihilates the vacuum, and that's the sum of a bunch of P pluses. If I look at the interaction, basically that's the difference between physical mass and the physical mass and the free mass, and P plus basically has to basically commute with both of these if they're both in the kinematic subgroup, which means P plus basically has to commute with the interaction. And if you basically push P plus through, basically it's got an interaction on the vacuum, basically it's an eigenstate of P plus with eigenvalue 0. If you start putting intermediate states in, the only P plus satisfies the spectral condition. The states P plus equal to 0 that are continuous of sets of measure 0. So the only thing you pick up is the vacuum. And so basically what that says is the interaction on the vacuum is proportional to the vacuum again. And if you look at m squared and write it in terms of P plus, and this is going to be P minus P plus plus P perp squared. P plus and P perp basically annihilate the vacuum. So this is 0. And M0 also annihilates the vacuum since M0 commutes with V, it annihilates the vacuum. What you're left with is V squared. That's every application of V gives you the vacuum back. So what you end up with is essentially 0 is equal to essentially V squared times the vacuum. And that means that's the damage. So basically, you basically get that the vacuum doesn't change. This is an argument of people in the field. On the other hand, this sort of ignores the fact that the reason you have interactions in the vacuum is because there's a part of the field that has 4 creation operators or multiple creation operators. And those things basically, when you start normal ordering, you're still going to basically change the vacuum. If we look at, say, phi to the 4th and look at what happens on the light front, you find out that, in fact,
there's something very singular going on there. The piece that has four creation operators has a 1 over p plus squared in the denominator. And if you multiply p minus times p plus, you might think that annihilates the vacuum, but this thing kills one of the p pluses. You still have something singular. So basically, the argument I gave before basically breaks down. And on the other hand, you're going to eventually you have to. This obviously isn't the right answer. You have to renormalize the theory to figure out basically how to regularize this thing. And so there's some work that has to go to actually write down the full interacting theory. So basically, if you do that, and you normalize the theory properly, you should get something that's well behaved. And so basically, while the true vacuum is not trivial, if you finally can write the theory in terms of this algebra of fields on the light front, basically, you evaluate things there, like I did with the axiomatic case, then in fact, you can use any vacuum you want, as long as you're working in the right subalgebra to calculate your vacuum. Even though it's not trivial, it behaves trivially when you calculate things, or it can, depending on what you're doing. Ill-posed initial vacuum value problem. This is kind of interesting, but what's going on here is, if you remember, if I have this kernel here, if I push my p plus evolution through that, it becomes the light front Hamiltonian. And so my fields, my Heisenberg fields can be expressed in terms of fields on the light front. And if I look at what happens, basically you're putting the P0, the P minus part, you're replacing it with this quantity on the light front. And if I go to the next slide and look at the Heisenberg fields, where I basically am looking at a dense subset of test functions here, namely functions with compact support. So the P0 and the vector part of the momentum are basically have to vanish with these quantities less than some r squared. That means basically P plus and P minus are bounded. In this case, that's a dense set of vectors. And if I'm looking at what happens with x plus evolution here, I guess it would be shifting x plus to 0. So I guess here. We look at the Taylor series and start pushing things through. This function is going to vanish unless this quantity is less than r, so this is bounded. If you look at the series of different things together, you find out that in fact this is exponentially bounded by essentially a constant. And that means that x plus evolution actually converges on the dense set here. So basically, once you basically restrict to the subalgebra that basically has the mass shell condition in it, you never pick up these quantities that are connected by light line signal. So you basically have convergence on this. And I said there's no problem with the initial value problem. What am I doing for time? I guess I'm running out here. 2 minutes? Yeah. Okay, I better take care. Let me just rotational covariance. The interesting thing about this is that you take P minus and the kinematic generators, you can't get back to the rotation. Then if you take the transverse rotation, you construct P minus in terms of kinematic generators and J1. So basically, these things basically give you the dynamics back. P minus and the kinematic generators don't give you enough physics here. I'll just mention there's some constraints on these guys. But the point is that you need some physics, and basically look at what happens when you rotate the light front. And this is stuff Volodya really talked about a long time ago. If you want things to be consistent, that's equivalent to rotational covariance. And that mixes ultraviolet and infrared singularities, which means basically any singularities in P plus are going to be singularities, have to be renormalized consistently with singularities in ultraviolet singularities. And you want to do that consistently, you need to do that consistently to basically get rotational covariance as well as space reflection covariance. I will stop here. I was going to talk a little bit about spontaneous symmetry breaking, but it's very similar to what happens in the vacuum. And if anybody wants to talk about that privately, we can do it during the coffee break. Thank you, and appreciate the invitation.
Questions to Wayne? James, Pacheco, and Lugo.
That's very interesting. Hiller and Shabasheva have addressed the 5/4 field theory problem and made, along with Burkhardt, tried to make a connection between the equal time or covariant and the light front. And they found out that they had to develop an effective Hamiltonian, their most recent work. And the effective Hamiltonian is a highly non-perturbative correction to the ordinary quantized Hamiltonian. Is that procedure, which then makes it a very involved calculation to try to put back in the effects needed to make the comparison. The interesting thing is equal time or covariant and light front both produce phase transitions, but they do so with unequal mass parameters. And that's their ultimate story, is to try to relate the renormalized masses of the two theories to each other.
So, I mean, in terms of just, rotating the light front, you know about the mass when you do that, and you get a reasonable limit then. Oh, yeah, when you rotate the light front, or, rotate, your quantization surface, towards the light front, about the mass as you're going there. That information get lost if you start on the light front, but as you approach the light front, actually it works fine. And you can see this in the 2-point function. If you take the limit of the 2-point function, as you get to the light front, you get something with the K1 Bessel function and all this stuff. Whereas if you start on the light front, you get nothing basically. And I don't know exactly, what John and Sophia are finding, but if you do it that way, you're going to get the right answer. And you'll have to basically do some building what's on the light front. And this is what I would argue is equivalent to finding the right subalgebra. Essentially, it puts in the dynamical mass shell conditions, which are much more complicated than you get in the free field. These are the ones you'd have to get with the infields and stuff. And, in my case, I'm not constructing those. I'm just showing you that if you assume the axioms, those exist. Yeah.
Hi, nice talk. So, and then I know you're formal way. What do you happy to solve the zero mode problem? Because you are very formal, but a practical way. Why help your formalism to solve the zero mode problem in light front?
Yeah, well, I mean, my understanding of the zero modes is you look at rotational invariance, okay? If you just look at P minus and renormalize that, that is not enough physics to get the J-perps right. Turns out there's a lot of J-perps that you could use that are consistent with that. And so there's some missing physics there. If you start with a canonical theory or a covariant theory, you get the rotational covariance right. So the question is, you've got to renormalize the theory. And one way to get rotational covariance is to basically look at different light fronts and basically check to make sure you get the same answer by quantizing on different light fronts. And that looks trivial, but when you actually start dealing with bound states and stuff like that, there's some way you have to match things up carefully. And it's you do the matching on one light front, you have to do the matching on another light front. You want to make sure that the matching's done consistently. And so to do that, there's when you change light fronts, you're changing P plus to an ultraviolet singularity. So basically the issue is, when you do that, you've got to renormalize P plus and the ultraviolet singularities consistently. And to get the rotational covariance back, I would argue that's where the zero modes come in. I mean, Lubo may have something to say about that.
Actually, I have an independent question. You showed the term in the Hamiltonian of lambda 5/4 composed of a dagger, and there is a singular 1 over P plus squared. I never noticed that, to be honest. How does this emerge? Because usual argument is that we have a delta function which vanishes because naively all lines carry vanishing P plus.
There's a delta function on top, but there's a bunch of these momentum fraction things that multiply by P plus, and that gets factored out. That's where what I just showed was the part with 4 creation operators.
Yeah.
You just naively calculate it. Assuming, you're just doing canonical free fields, but with phi to the 4th, and you find out that's what you get by naively calculating.
But the delta function will eventually kill this term.
Yeah, the delta function is still there, but
I mean, there's is it? Yeah, there's a delta function still on top. Okay. But the problem is that this thing's not a distribution. Delta P plus over P plus squared is, is just a bad object.
Thank you.
Okay.
Any more questions to Wayne? I cannot resist to ask you one question.
Sorry, I ran over. I thought I timed this a couple times. And
okay. You mentioned about, symmetry breaking.
Yeah.
We know, if we think on QCD, quarks are heavily dressed. And I'm wondering, I remember one of your papers about Haag's theorem. So you essentially used, operators, it looks like that creates and annihilates. Mass particles that are that are free particles, essentially. How we manage that? You could say.
Yeah, you have creation and annihilation operators. The problem is on the light front, those are all the same for all different theories. Okay, so they don't really constrain the dynamics at all. And the point is, if you look at all the ways you different smearing functions you have, there's a subset or a sub-algebra of those basically that give you that essentially you put things on the mass shell. Okay, and those are all different. And that's where the Haag's theorem comes in to some extent. The inequivalence comes when it all ends up in the algebra. And this also relates to spontaneous symmetry breaking. The charges on the light front have no dynamical content at all. And you really have to find a way to go off the light front. And different people do this different ways. If you look at, for instance, what
what's your microphone?
Oh yeah, trying to think, I can't remember the names of all the people, but there's different ways of either using the generators or using ways of coming off the light front, and then you find out you can recover the usual charges. But the point is, if you use these subalgebras, you can build the operators that you need to basically couple the vacuum to the Goldstone boson. There's another issue there too, basically, that the charges themselves are not necessarily well defined because you're integrating over an infinite surface of a local field. But the Coleman has this nice commutator function that basically cuts things off. That doesn't work on the vacuum either, on the light front, but that's still irrelevant compared to, you still need these subalgebras. So.
Any more questions to Wayne? You still, Lubo, you are going to talk soon.
Yeah.
Okay, so let us thank you, Wayne, for the nice talk.
Apologize for running.
Yeah, thank you. Lubo, please. Now is your turn. I knew that. Okay, this one, that's okay. And this one.
Very much. Please again. My topic is some effect similar to microphone.
Yeah, it's not working. No, you cannot put inside the pocket. Yeah.
Okay, I thought I'm close enough.
No,
to the microphone.
Okay. See.
Similar problems.
Not working yet. Maybe it's off.
Oh yeah. Okay, thank you. When used more rigorous language of axiomatic field theory, I will analyze or try to give some solutions of similar puzzles or subtleties. I prefer to call them subtleties because I believe that the light from field theory eventually is healthy and we should find all solutions to these puzzles. But my methods or technique is much more simple-minded. It will be ordinary field theory. However, I will pay attention to some mathematical details, and I will try to be careful enough. And my results will, in some sense, be different, at least to some extent. Because before I concentrate on the 2-point function and its several limits, I will try to give you a new picture of zero modes, light from zero modes, namely dynamical ones. A brief introduction. Sorry. Here is my outline. I will remind you briefly the main properties of light from field theory. Then the zero mode part will come. I will develop the quantization of two-dimensional massless scalar field, and we'll try to convince you that actually it's quite relevant for 3+1 dimensional cases, including the gauge field. I will briefly touch the operator solution of the Turing model in a new formulation, which means that there is a gauge fixing term in the Hamiltonian, and this makes the model closer to the Schwinger model. I should say that I don't think that we have solved the Schwinger model in the light front field theory, and it should be, and it is a testing ground which should be solved if we believe the light front is a reliable scheme. And I will also show you how the two-point function can have good or well-defined light front restrictions and some other limits also. This implies presence of damping factor in the field expansion. And finally, I will comment on the recent claims in literature that the light front Hamiltonian field theory is not able to correctly predict the two-point function at coinciding points. That is, x plus going to zero limit. We know that everything started with Dirac in 49 with his classification of relativistic Hamiltonian dynamics, several forms. This framework was developed into more strict or rigorous quantum field theory by people like Lochwiller, Clausen, Streit, Good and Soper, etc. So by light front quantization, I understand quantum field theory with different choice of the space-time and field variables as compared to the usual field theory, which I call space-like. Here is my conventions. Of course, there is a well-known property that both P plus and P minus are related without the sign ambiguity in this rational function. So both can be taken positive. This is an important property of the light front scheme. Wayne already discussed the distinguished features of light front field theory. Of course, because of positivity and conservation of P plus in the usual way of thinking, there are no terms in the Hamiltonian composed solely from the creation operators. So in fact, this leads to the statement that we have a consistent Fock expansion on the trivial vacuum in the light front field theory. Let me mention a few weak points of the scheme from my point of view. I think that the development of the front form of quantum field theory was rather non-uniform and non-linear, and we still do not have a compact formulation of light front field theory. Actually, the very fact that we are talking about some puzzles or subtleties is telling that. There have been claims in literature that the light front theory has certain drawbacks which are not present in the usual formulation, that light front field theory evaluates some essential principles, including Lorentz invariance. This goes back to the work by Nakanishi, Yamawaki, Tujima, Yamawaki in the 70s and 80s. They also claim that light front field theory fails in some aspects, that is like equal light front time projection of the two-point function does not exist, or is ill-defined, or is inconsistent. And also there were troubles with the two-dimensional quantization of two-dimensional massless light front fields, which maybe is not the biggest physical problem, but actually we should really solve all problems starting with the simplest one if we believe that the light front quantization is a is a reliable scheme. So also there claims that there are some new singularities for p plus equals 0. My optimistic explanation is, or interpretation is, that the structure of the light-from field theory is completely consistent. We have just not found the correct formulation of these subtle points yet. Sometimes we are led by intuition and patterns which are obtained in the usual space-like form of quantum field theory. One example which I will remind you is the problem of vacuum bubbles in perturbation theory. It's interesting that already in the 70s, people like Chang and Ma and Yan actually used Feynman rules in light-front variables and found that one should be careful with mathematics if one wants to get the covariant answers. But it was later found that the old-fashioned perturbation theory was not able to reproduce this, so there is a clear contradiction. And Collins and Dorokhov and myself, we found a way how to get back these vacuum amplitudes in light-front perturbation theory. Now I will switch to light-front zero modes. I will give you a very brief introduction. We should distinguish between the constraint and dynamical zero modes. Usually in 90s, when this was a hot topic, people regularized the theory by enclosing the system to a finite volume within minus LL and minus L perp. And essentially the zero modes, of course, are Fourier modes of the field which carry p plus equals 0. So in the case of the scalar field, we separate phi naught, which has no x minus dependence, and the rest is called the normal mode field. And this was first noticed by Nakanishi and Yamawaki. Of course, the real reason for this is that the Lambert operator in the light-front formulation has different form. It's linear in light-front time derivative and d minus. So then in, for example, lambda 5/4, we can find the constraint for this component phi naught, which is very nonlinear, and people have tried to solve it, this constraint approximately, and saw some signatures of symmetry breaking in the light-front formulation. The other type of zero modes is a dynamical zero mode, which is corresponds to an independent, dynamically independent field component. For example, it's present in QED 3+1. Of course, even this mode or this problem of dynamical mode was not completely solved because it's just one mode, and it raises questions because if we naively assume the relation between dispersion relation between p plus and p minus and have non-zero p perp component of this mode and non-zero mass, then for p plus equals 0, naively, this mode corresponds or carries infinite energy, light-front energy, which is kind of not very physical, although some people believe that it's the fact of life. But anyhow, this mode in the usual description is just one Fourier mode, and if we insist on particle interpretation, so this mode actually has vanishing in the gauge theory, has vanishing mass, vanishing p perp, vanishing p plus, so it's rather ill-defined. Its energy is ill-defined, 0 by 0 divided by 0. That's what I meant. Okay. Now, my third part corresponds to massless light-front scalar field, a mu field, gauge field, and a fresh look at zero mode. So now I come to the new development, which I believe can potentially explain some of these problems of the zero mode. So let us look at a very simple problem, two-dimensional massive light-front scalar field. Of course, this is the two-dimensional Clyde-Gordon equation. We can solve it easily because it's a free field. in terms of creation and annihilation operators with the commutation relations of this form. Sorry, of this form, usual ones. But now imagine we have zero mass from the beginning. Then the field equation is just d plus d minus on phi naught of x equals to 0, which obviously implies that phi naught has two components. One is phi of x minus and phi 0 of x plus. Usually these fields have been considered as arbitrary, but what we did with Pierre Granger was that we considered the massless limit of the massive field. And actually this works, because when we look at this expansion, we can set m or mu equal to 0 from the very beginning, and we actually get the x minus dependent part. So it's like function of operator phi of x minus. The question is, where is the other part? Where is the phi naught of x plus? I don't have time to go into details, but one can change variables and actually get the second part. And I will bring you arguments why such a component is mandatory. It must exist because of some arguments related to two-point function and its limit. So what I'm saying is that one can find the component phi naught of x plus, which is a very similar structure, like similar to phi of x minus, but we have different set of creation and annihilation operators, and there is a dependence of x plus instead of x minus. Why this is necessary or why this is mandatory? Let us look at the two-point function, which I call d2 plus, which is phi vacuum expectation value of phi x and time derivative of pi y. It can be evaluated in lifelong coordinates, of course, in terms of Bessel functions k1, y1, and j1. And as a long time ago has shown Bergnoff in a similar context, there is a massless limit which is non-zero. So this two-point function with non-zero mass has non-vanishing massless limit. So this implies that we should have a field which I call phi naught, which actually reproduces this. That is, it's a massless field. And this is precisely parallel to the problem which I already indicated, namely, if you set mass equal to 0 to the massive solution, we get phi of x minus. We can compute the massless limit of this object, phi x d minus phi y, and it will just be the same as the two-point function calculated from massless field, which we obtained. The only difference is that we had to be more careful in identifying this phi naught of x plus, but otherwise the story is the same as phi naught y plus or x plus. Now, if we look at 3 plus 1 dimensional situation for the massless scalar field, so this is the light from the Klein-Gordon equation, and obviously this solution, this phi of x minus and phi 0 of x plus, sorry, this is wrong, it should be x plus, actually also satisfies this equation. So I'm saying that the light front field, scalar field, massless, however, not only has the standard piece, which depends on all 4 coordinates, but also has this would be 0 phi of x minus and the true 0 mode piece phi naught of x plus. They simply satisfy, okay? Now, let us switch to gauge field in 2 dimensions. The interesting point is that if we add the gauge fixing term in 2-dimensional Lagrangian, we get in the light front coordinates this simple Lagrangian. And my goal is now to find A plus and A minus in 2 dimensions. And as I mentioned, for the case of the scalar field, we should start from the massive field. So we add a small perturbation, like massive vector boson, look at the Lagrangian, and find that the B field satisfied also the Klein-Gordon equation. So we have a similar situation. However, in this case, we have densities which have wrong signs here. And the only consistent way to get correct form of P plus and P minus is to assume a relation between B plus and B minus, namely that B minus equals to minus B plus, because it also satisfies the canonical commutation relation B plus between B plus and P minus. So this choice is the consistent one. Otherwise, the theory would not be correct from the point of view of particle interpretation. Once again, we are in the situation as we had for the scalar field. So my expansion for B plus field is similar to the scalar field. And as I said, with the condition between B plus and B minus, we have the Poincare generators P mu, which have the correct form. It's indicated here. And now we can take the massless limit. And I'm saying that this is what this limit actually defines the two-dimensional gauge field, which has two components. In the light front description, one again only depends on X minus and the other one on X plus. And in analogy to the scalar field, we have the two sets of creation and annihilation operators. One corresponds to A plus X minus, the other one to zero mode. And I call it C tilde. Of course, here is the X plus dependence, here is the X minus dependence, and the commutator between them is vanishing, so they are independent. And the resulting Lagrangian is written here. Of course, I understand this very, very primitive, simple-minded or simple situation, but we need to understand this simple point. Technically simple, but I believe we should conceptually understand the zero modes better. Now we have, for the massless case, that is for the A field, we have P plus and P minus. This P minus has to be obtained as a massless limit of the massive field, as I already indicated, but it's given in terms of C tilde and C tilde dagger. And one can now check in a very simple calculation that any states of the form C dagger acting on vacuum, C dagger acting on vacuum have finite energy, light on energy, and vanishing momentum. That's why I'm talking about the zero modes. So this might be a framework for description of the light from vacuum degeneracy, perhaps later. Now one can repeat this for the 3 plus 1 dimensional case. But before that, yes, I would like to make two remarks concerning the light from zero modes. First is that we should really keep in mind that for the massive field, let's say in 1 plus 1 dimensions, the zero mode projection simply tell us of the field equations, tell us that mu squared phi naught of X plus equals 0. So for non-zero mass, the zero mode is vanishing. This is what I said at the beginning, that I was considering only massless scalar field equation or Klein-Gordon equation. Also, sometimes people work with Feynman diagrams evaluated in terms of the light front variables. In that case, K plus and K minus interval is between minus infinity and plus infinity, and sometimes the contribution indeed after dk minus integration, the contribution for some amplitude, including the vacuum amplitude, for example, is given due to delta of K plus. That is kind of zero mode, but in the genuine light from field theory, I mean the perturbation, light from time-ordered old-fashioned perturbation theory, we have a different interval. We have P plus and P minus strictly zero, or maybe sometimes equal to zero. So this mechanism does not work. So the zero modes, K plus equals to 0 in the Feynman, light from Feynman, and the usual genuine light front are different, I believe. Now the 3 plus 1 dimensional case, it's nothing but a canonical quantization in the Feynman gauge. In the light front, I could say make some comments, but the main point is that as we had in the scalar field case, I'm saying that we again have two-dimensional fields, which are admixtures to the normal mode field. So even in the continuum formulation, we can talk about zero mode component, and maybe this could be physically interesting. There is another, so these, I will of course not show you these details, but one can go through the canonical quantization. And the important, from my point of view, point is that actually in the light front covariant gauge or Feynman gauge, there is no analog of Gupta-Boiler condition, because again, we have to have this condition, this condition. Otherwise, the Poincare generators would not work. So in the usual space like QED 3+1, A naught acquires due to the gauge fixing term, the non-vanishing conjugate momentum. This is not the case in the light front situation. And I believe this might replace that condition, but probably we don't have to talk about indefinite metric Hilbert space as in the Gupta-Boiler. Okay, I don't have enough time. This is the section where I wanted to give some illustration of these two-dimensional fields or zero mode fields at the level of the simple model, Turing-West model, in the situation or in the formulation where we have a gauge fixing term. So this has not been done in the light front before, but I have to skip this. What I want to tell you that one can obtain the operator solution of the system of coupled field equations, which are written here. So these solutions are given in terms of massless Fermi fields and massive B fields. And due to the presence of the gauge fixing term, this might be closely related to the Schwinger model, but it requires some extra work, of course. It has not been done to the very end. Now a few words. So these are components of the solution of the Turing-West model. Now, light front restriction of the two-point function. I only can point out that if we set time equals to 0 at a free scalar field, we maintain the mass dependence, because the mass dependence is also present in the factor of denominator. Naively, if we set x plus equals to 0 in the light front field expansion, we kill completely the mass dependence, because usually people have these plane wave factors. What I want to emphasize is that if one adds some damping factors of this form, actually all the troubles related to the light front restriction of the two-point function and of the commutator function in two dimensions, as well as in 3+1 dimensions, go away, and this can be shown even at the level of interacting fields. These epsilons, which are regulators, actually keep information about the mass. So here is the calculation of how one can recover the equal time limit of the Pauli-Jordan function for a scalar field. One needs to consider the expansion of the corresponding Bessel functions for small value of the argument, and everything works. There is another interesting point that actually, if we use the expansion, large argument expansion of this Bessel function, we recover, instead of sine function, which is actually the flat function, plus or minus 1, we get the damping factors. This was noticed already by Nakanishi and Nakanishi-Yabuki a long time ago, but my argument is more, I believe, is more systematic, because they just propose this ad hoc solution to the problem of restriction of the two-point function and two-point function obtained from the restricted light front fields. I think this is required by mathematics. In order to have well-defined integrals, we have to add these damping factors in the field expansion. This is the 3 + 1 dimensional case, which is completely parallel to the 1 + 1 dimensional. And last few seconds I will spend on another application or another evidence that this damping factor or smearing factor is very important also for the equal x limit of the 2-point function in the light front representation. So previously people have considered the time order. There is Feynman actually propagator 2-point function with 2 orderings, with the result that because of the fact that the Hamiltonian form of light front field theory does not contain the circle at infinity, which is present in the Feynman light front. So the Hamiltonian form actually misses some information. And I'm saying this is not quite true, because if we keep both epsilon plus and epsilon minus, which I insist must be there, then the limit of this 2-point function actually behaves like 1 over epsilon plus epsilon minus, which is actually quadratically divergent. In the K representation is lambda squared, of course, and this is the case. We know that. And the problem, I think, our colleagues had was that they, after all, considered the integral in many specific formulations, but still it was, the main object was this kind of integral, but they had lambda equal to 0 from the onset. And this object is singular, because if you evaluate this for lambda equals 0, is big, or lambda tending to 0, it's 1 over lambda. So I think one should work with well-defined quantities, and if one does so, the light from Hamiltonian formulation simply sees the correct answer, which is divergent, but epsilon plus and epsilon minus, which are present, keep this object regular or regulated. So my conclusions, I have tried to give you, to formulate a new approach to light flow dynamical zero modes. In contrast to the conventional treatment, it's a true field. That is, it has infinite number of modes. It's not just one mode. Of course, one needs to find applications or see how it works in some practical applications, some models, dynamical models. I also try to show you that some apparent difficulties in the front form of the relativistic dynamics can be cured if one is careful enough about mathematical details. And I believe this is the end of my talk. Thank you very much.
Hello.
Questions?
Hello.
Okay, questions?
Hi, Rob. Thanks for the nice talk. I know I say K plus 0 is not the, if you approach Feynman diagrams, it's not genuine light front, but Feynman diagrams coming some Lagrangian, or you can make a Hamiltonian formulas. That's, then the light front is there. I don't know. You can.
Okay, the difference is, okay, yeah. The difference, in my opinion, is that it's how you define your perturbation theory. In old-fashioned language, you have only, you so to speak, have the K minus integration already done at the beginning. You don't need to worry about it. It's built in, and the language, it's non-covariant form, but Feynman is different. And when you go back from Feynman to three-dimensional, you need to do some, some contour integration, and this actually brings back some difficulties. I think if you start from the genuine time-ordered light from perturbation theory, you avoid these extra troubles.
you have zero volt, then you take more time consideration.
If you evaluate light front integrals of the Feynman type, you have different mathematics compared to when you evaluate old-fashioned perturbation theory. You have different integration domains. So I think, of course, physics, the amplitudes are the same, but the mechanism is different. And I wouldn't call the Feynman, I mean, in the light front Feynman diagrams with k plus equals 0, that these k plus are the same. To me, they are not the same. They are not the genuine light front, because in the light front perturbation theory, if you formulate it from scratch, you have to insert complete set of intermediate states, you see, and then you work explicitly with the modes which are present in the light front. And these must be different from Feynman.
Naive question. In perturbative calculations in Light-Cone gauge, there was a prescription by Liebrandt and Mandelstam. Is that relevant or useful in this context at all?
You know, I don't know. This is the simplest answer. I remember at the beginning of the 90s when this was a hot topic, on the Light-Cone meetings, but I'm not an expert in this, and in my observation, this is not very, so to speak, hot topic nowadays. I don't know what was the story of this, how this ended, or if it's, sorry, I don't know what happened.
More questions to Lubu? So Lubu, we would like to thank you and thank all the speakers. So 2:30, so it will be closed, this room, up to 1:30, okay? We will see. I will ask the secretary. 1:30 will be open. Jamé, just wait. Just wait. Yeah.
Good afternoon, everybody. Ready to start? So, yeah, you have to
put all
yeah, so do something with that.
Yeah,
And I can help you with.
What is that?
Oops.
This is for the button. Okay.
Excuse me. Okay.
It's okay?
Yeah. Okay. So let's start
Can you
the
hear?
afternoon session. We can hear you very well. Thank you, Jean-Marc.
Yeah.
It's here. This is the light, and this is for forward, and this is backward. This is the light.
Light. Okay.
Okay. Thank you.
Can I start? Okay. So I come from Paris. I was in the, this is the new name of the old laboratory, which was Institut de Physique Nucléaire d'Orsay. We changed the name in honor of Joliot-Curie, Irene, who founded the laboratory. And this is a work in collaboration with Volodya Karmanov, a young researcher in Lebedev Institute, and Agop Sajjan from the same lab. I will talk to a very simple problem. Is the Bethe-Salpeter equation for a scalar particle. So it's very, very easy two-body problem. So Bethe-Salpeter equation deals with a pre-existing object, quantum mathematical object, which is well defined in quantum field theory. And this is a great advent. Is a vacuum expectation volume, so it can be computed in lattice, and is very, very well defined from the quantum field theory. But it's a nasty object because if you look into the Minkowski, it's plugged with singularities everywhere. So it's not a wave function. It's a strange animal, but these guys obtain an equation for them which contains the total mass of the particle. So P squared is the total momentum of the two-body system. And this is an equation to obtain P squared as a function of the coupling constant. So it is very useful. It was the first relativistic two-body equation for bound state, non-perturbative. So in principle, here you have the free propagator, here is a kernel, and if this kernel contains all the irreducible graph, solving that equation will be strictly equivalent to solve the quantum field theory. But of course, there is celestial music because nobody is able to give this kernel that contains everything, because it's also a lot of infinities. And so in practice, we use that with a very poor restriction of the interaction kernel. And furthermore, we solve it in the ladder, at most cross-ladder approximation. So now we will consider the solution of this equation with two particles, which are scalars, and which exchange either a photon, so zero mass particle, which gives in the non-relativistic limit the 1/r potential, Coulomb-like, and this natural extension to the Yukawa potential. So alpha, we will use instead of J, which appears in the Lagrangian, alpha, because of obvious, in case of QD, is 1/137. So the massless case, this case, the Coulomb problem, has the peculiarity to accept solutions that have no counterpart in the non-relativistic limit. So when you consider this solution for small binding energies, it coincides with the Rodinger equation, but there is another family of solutions that in the Rodinger equation disappear. So this equation was solved first by Wick and Kutkowski. Here is the place where he introduced the famous Wick rotation to solve all that. Practically the same year that the Peter-Salpeter equation was produced. So we are very much interested on these strange solutions that has no limit equivalent in the non-relativistic limit. And this was already presented by Karmanov in the last Light-Cone meeting. So this was his state, and this was in École Polytechnique in France. So the aim of this, my contribution or common contribution, will be first briefly summarize the results of the massless case, the Coulomb-like, and then present our new results for the massive exchange, the Yukawa, to see what happens. So the massless case, is a pure Coulomb problem. So this is a kind of implicit eigenvalue equation, because if you put a given p square, you obtain the coupling constant as the eigenvalue. So it's a little bit not standard one, but is in practice is an eigenvalue equation with the coupling constant being the eigenvalues. So for a given m square, there is a discrete set of coupling constant that solves the problem. So you can obtain m, the total mass of the particle, as a function of the coupling constant. Instead of m, we use the binding energy, which is given by, well, in this way, is the difference to the 2m. And instead of j, we put alpha, which corresponds to the structure, final structure constant in the Coulomb case. So in the non-relativistic case, this is trivial. It's a parabola. The b dependence on alpha square is just a parabola. So it's trivial. And we are going to look either in this direction, fix the binding energy, and see the different coupling constants that solve the problem, and that corresponds to the ground state, first excited, and so on. Or in the other way around, fixing alpha coupling constant and obtain several binding energies. So the contribution will only contain this kind of figures, but in the other side. So we will look not b as a function of alpha, but rather alpha as a function of b. So you turn your head and everything will be clear. So Wick and Kutkowski found that this model had indeed a family of solutions, phi n, so to say, eigenfunctions, which just are not eigenfunctions, Peter amplitudes, and energies that for small values of alpha coupling constant and so forth were tangent to the non-relativistic limit up to some logarithmic corrections. It was very satisfactory because, I mean, non-relativistic should be a normal case of the relativistic equation. But for each value of n, for each Coulomb state, they found an additional infinite series of solutions, which were labeled by another quantum number, kappa, which goes from 0 to infinity, due to this special symmetry of the Coulomb problem, which is SU4 symmetry. So there are two quantum numbers. So the eigenstates, eigenenergies, contains the normal n, which gives the Balmer series, and kappa, another. So if kappa is 0, we obtain En0, which is the usual Balmer series. And what about the rest of these states? So it was shown first by these Italian guys from Pisa that if kappa is odd, these states do not contribute to the S matrix. If zero is matrix for these states. So we have to concentrate only on the even states. Kappa equals 0. Kappa equals 0 is already easy, is the normal Coulomb states, and kappa equal 2 is the first. So what about that? So here is the spectrum of all these states. It's a little bit confusing. So it's the same than before, but turned 90 degrees. So here is the coupling constant, alpha, but instead of alpha, you put lambda alpha divided by pi, because it's much more easy to identify a value lambda equal 2 than pi. But pi is very complicated number. So you see in black correspond to kappa equals 0, the Balmer series. This is the states, the black ones, that for small binding energies coincides with the Coulomb states. And you have n equal 1, we are not, kappa equal 1, we are not interested because they are 0 in the S matrix, but kappa equal 2, here I put k, is kappa in fact, okay. The green one, you see that when B goes to 0, they don't go to 0. They go to a finite coupling constant. This is totally strange. For a massless exchange, this is totally, I mean, the particularity of a massless exchange, like Coulomb, is that whatever is the value of the coupling constant, you have a states, an infinite number. Here we found some solutions that even at 0 binding energy requires a strong value of the coupling constant. Very strange. So instead of having an accumulation point at 0, like for the normal states, all the others go somewhere, and that's why they were called abnormal by Wick. I show you the same, but in a log scale. You see very clearly here the normal states is this ensemble of n equal 1, 2, 6, which will go to 0 very slowly, but go to 0 when B, and the other family of states go to a relatively high value of the coupling constant, as in the massive exchange. So how can be that the same model produce such two sets of totally decoupled states? Here is the same in a log-log zoom, the zoom of the zoom. How you see here the family of the usual solutions. This is a non-relativistic on dash. So you see that the beta-salpeter solution really are tangent to the non-relativistic one when the energy is very small, but you have to go very low in energy to coincide. And the other ones are very far away. And in fact, all of them will also tend to another point, but which has nothing to do with that. So if the normal states exist for any value of alpha, of the coupling constant, building an abnormal state requires a strong value of the coupling constant, even at 0 energy. Very surprised. So for these abnormal states, the coupling constant, instead of going to 0, when B goes to 0, tends to 1/4. When you divide by pi, that's why we introduce pi to divide the coupling constant, because it's more easy to identify 1/4 than alpha divided by pi divided by 4. And the way in which they tend to 1/4 is that. So these are the different states, coupling constant as a function of the binding energy for the abnormal state. They go indeed to 1/4, which is here, but very slowly. This is 10 to the -6. You still means a factor 2 with respect to the asymptotic value. So this is the relevance of the factor of this value 1,4 is the limit of the coupling constant when the binding energy goes to 0 for these states. Now, there is another interesting value of alpha divided by pi, ln, which is 2. And what is the meaning of that? It's simply that when alpha equal to pi is the value of the binding energy equal to 2 mass. 2. It means the total mass of the, if I represent not the binding, but the total mass vanish. So when alpha equal to pi, the two-body system has a 0 mass. And of course, what happens after? In fact, the equation, beta-salpeter equation, is not sensible to the mass, but to the mass square. So if we are curious enough to go beyond m squared equals 0, we see that in fact, m squared becomes negative if you continue to increase the coupling constant. But then we are in a strange world with tachyonic solutions. M squared negative means that m equal imaginary, and okay. Some people like these kind of things. We are a little bit not very confident, so we want to avoid them. So in order to avoid them, we have to limit the coupling constant to 2 pi. Then this model introduced this kind of equation solutions. So to summarize the case, the Coulomb case, mu equals 0, if one does not take care about the tachyonic states, the normal solution exists for any value of the coupling constants, and the normal solutions only for alpha greater than p over 2, which is lambda greater than 1/4. But if we want to restrict to the non-tachyonic states, if we want that in our model, these m squared negative solutions are not there, we have to limit it alpha, the coupling constants, to 0 to pi, or lambda to 0 and smaller than 2. And the abnormal states are then limited to this place. Now, these abnormal states are always has always very small energies. If you remember that, here, the binding energy is always very small. In fact, it's limited, is smaller than 0.0, where it is. No, I am going in the reverse way here. Are limited to B divided by in constituent mass units. So for the nuclear case, that will be 9 MeV. So always limited to very small binding energy. Now, the existence of this minimal coupling constant for a bound state is typical from a massive exchange. Even if we deal with Coulomb problem, this new state, the abnormal states, behave as if the photon became massive in this sense. And what is the mass? The typical mass is 400 MeV in the nuclear case. So it's a little bit crazy. Now, how to characterize these abnormal solutions, apart from the fact that they are very decoupled from the rest in the spectrum? We don't want to look to 200 states to have an idea of what is the physical content of these states. So how to characterize, apart from the behavior in the energy? This was the main result of our contribution to that. So the state vector that appears in beta-salpeter equation is a quantum field theory state, which involves all the Fock components on it. So because there are two interacting particles, but you develop by the Lagrangian all the Fock components. So you have 2 body, 3 body, 4 body, with constituent particles and also the exchange particles. And the total norm of the state is the sum of the contribution from 2 body, 3 body, 4 body, and so on and so forth. Now, on one hand, we are able to normalize, if we compute the form factor, we are able to normalize the state to 1. And on another hand, we are able to compute the 2-body contribution to the total norm. How? We take the beta salpeter amplitude and we project it into the light front, and we obtain the 2-body component of the focus space. And with that 2-body component, we compute the norm of the 2-body pair. And doing that, we found very striking difference between the normal and the normal solutions. In the normal states, we found that the 2-body contribution tends to 1 when the binding energy of the system tends to 0. So you take a non-relativistic system, and essentially is a 2-body state. So cuckoo bar or NN bar or whatever you want. While for the abnormal solutions, when the binding energy of the state tends to 0, and I remind you that they have always very small binding energies, these states, then the 2-body norm of the state tends to 0. So what are these states? They are many-body states, like in QCD for the proton. You have QQ bar, how many? As much as you want, QQ bar, QQ bar, QQ bar, and how many glues? An infinite number. And all that gives you the mass of 900. So these states contains an infinite number of components in the focus space. And at the low energy limit, the 2-body pair tends to 0, so exactly the opposite. This is a very non-trivial result. So, and that we published recently, last year. Whether or not these states survive in the massive case. So when, instead of using the Coulomb interaction, we use a massive now, massive exchange, a Yukawa-like. Do they survive? And the answer is the following. Yes, they survive, but it's a very complicated problem, because when the mass is not 0, the SU for symmetry is broken, and this kappa quantum number that identifies the state disappears. So how can we sure that we are dealing with a abnormal state if you have now a quantum number? So what we did was the following. We start with the mu = 0 case. This is the case we discussed previously. So this is the first, this is alpha as a function of the energy. These are the normal solutions. This is the first abnormal state, what we call the ground abnormal state, gas, to be simpler, but maybe a little bit dark, okay? So this is the first abnormal state in the mu = 0 case. So we sit on this line and we switch adiabatically mu. We start with mu = 0, and then we increase. So, okay, that I skip. We do it, for instance, for the B, for a fixed energy. For B = 1, we identify this abnormal state at mu = 0, and then we increase mu, and we see that it evolves, alpha increase, of course. It has even level crossings with the normal solutions, these one are normal solutions. All the states except the blue one are normal solution. So because there is no quantum number conservation, because it disappears kappa, there are crossings. So if we start with a eigenstate, which is here is the 6 excited states, when you increase mu, there is a level crossing and it becomes the 5th. So we cannot even rely on the number of excitation because the order of excitations depends on mu. So we have to follow that starting from mu equals 0 adiabatically and control the level crossings and so on and so forth. So we did it for this case. We've done it for another energy, lower energy. Here you see that the abnormal state, the blue one, at mu equals 0 is the 12th excitation, and it has a crossing, it becomes the 10th. So we have to follow all that. But here already we show that, in fact, for a very small value of the mass, this non-tachyonic abnormal state survives. Why non-tachyonic? Because alpha divided by pi is smaller than 2. The blue is below 2. So we really a regular abnormal state that survives on this range of mu values from 0 up to here, approximately 0.03, which is very small, but nevertheless. So if we continue and take a smaller energy, you see that the abnormal state has one crossing here, a second crossing, a third crossing. So it's very difficult. Start being a 14th excitation and has two level crossing, becomes the 12th. And you see that this abnormal state survives up to higher value of mu, still small, but higher, up to 0.05. So we played that game for a lot of energies, and we were able to determine the maximum value of the mass exchange in order that the abnormal solution for the massive case survive. A small value of the binding energy below 0.009 divided by the constituent mass, and the acceptable value of mu are up to, say, roughly 0.01. So, and this is the new result concerning the massive case. So we can collect all that in a kind of diagram that contains everything. Here is one line is for a given binding energy. So for a given binding energy, here, for instance, 10 to the minus 4 binding energy, and the line represents the set of parameters, coupling constant and mu, that this abnormal state can exist. So this was our main conclusion, and I come now to the final conclusion. So we studied the normal and abnormal solution of this Bethe-Salpeter equation for two equal mass scalar particles interacting via a scalar exchange with mass mu. For mu equal to 0, the normal state exists up to coupling constant divided by pi equal 1/4, which is equivalent to a fictitious photon of 400 MeV mass. If we restrict to the non-tachyonic ground state, the coupling constant must be limited to these boundaries, and the binding energies are always small. And these abnormal states have a genuine many-body character with a two-body norm that tends to 0 when the binding energy tends to 0. And for mu positive, this is or large results, these are normal solution remain. But of course, for very limited values of the change mass. Now in the physics, where can you find that? If you take pion and mass or nuclear mass, you are out. But if you take a very heavy quark and a pion, if you take one of the big quarks, what is this, the biggest quark, the top, I don't know which. And if you put that, you are in these numbers. Also, you will see that if the mass of the constituents, that I let Carmanos to discuss, if the mass goes in the right direction, and also in solid state physics, in solid state physics, everything goes very slowly, but the energy dependent on the momentum is like relativistic. So people use in solid states the Bethe-Salpeter equation, and it is not excluded that some of these states could play a role there, because the mass in solid state is defined by the coupling to the. So it can have some application with heavy quarks, very heavy, or in solid states. Okay, thank you very much for your attention.
Thank you, gentlemen. Questions?
So I'm curious, actually, this one is in the so-called ladder approach.
Yes.
So I was curious that by adding, cross diagrams or even more, people have attempted those, and what effect for these anomalous solutions?
I am also curious and eager to do it, because we have these kernels, but of course it's a problem of time. This cross ladder goes in the right direction.
Right.
Because it increases always in this model, because this model is always attractive. So if we include that, it will go in the last in the right direction. We have to do it.
Yeah.
We have also to consider what Volodya will present, the different mass.
Yeah.
And if we are courageous enough, the Fermion case.
Perhaps it's kind of really non-perturbative at the end.
Of course, of course. So this is the first step. And
thank you. More questions?
Jaume, I will ask to remind our discussions. And I mean, this abnormal state corresponds to, in this language of light front, to higher for components.
Yes,
so
essentially.
You have indeed, I mean, suppose if you go to the next one, you have two particles plus one quanta.
Yes.
So it's a three-body state.
Yes.
And so on. So this will be a kind of exotic, or maybe if we go to quark physics, this would be a exotic.
Of course, of course.
Yes, could even be.
Yes, but I mean, if you are courageous enough, you can compute the three-body. What we know, that is the two-body norm tends to 0. Yeah. So everything comes from the rest. But sorry, no, I mean, we have to compute how many cuckoo bars and how many gluons are in on the nucleon. Nobody is able to say it, even Lattice people. They put out everything, but to know the weight of each part, nobody knows. It's very difficult to get. Here is the same. The two-body tends to 0, and the rest contains everything, but
yeah.
I have remark concerning question of Tobias. Of course, we showed that two body is small, but one can ask, but it is three body or many body?
Yes, no, you don't know.
We know that. We calculated behavior of alternating four factors, and this behavior depends on number of constituents.
Yes, but you compute that for the normal solutions, no?
No, for abnormal also.
As well.
And we see that these four factors decrease very fast, not like three-body four factors, but like many body. Therefore, we make this calculation.
Ah, yes. I forgot about the form factor.
Anyone else? I don't see. So thanks, Jaume, again. And Vladimir. So now we continue with Vladimir. Okay, let me.
Yes.
So this you put in the book. And this year, it's difficult. Yeah.
Okay, I hope.
Yeah. Forward, backwards, light.
This.
Yeah, this is forward. This is
Forward?
backward. Yeah, forward. And then the bottom one, yeah, backwards.
Okay, thank you.
You're welcome. And the first one.
So I am very glad that this series of lifelong conferences continues after COVID break, and I am indebted to organizers for opportunity to speak here. So I will again also speak about abnormal states, which were discussed at previous talk, and after this talk I don't need to repeat what they are. And so only two transparency. So we have the following situation in the Coulomb system. We have usual Balmer series. Okay, and solving mid-Salpeter equation, we found not we and Katkowski, we found another solutions which are absent in non-relativistic limit, and therefore we should understand what they are and maybe to give some predictions for experimentalists how to find them. So the situation is the following with the spectrum. We have Coulomb spectrum. This is energy and a lot of levels, Coulomb level coming to zero when n increases quantum number, and starting with some energy, there is another series, Coulomb series continues, and there is another series which also goes to zero, infinite number of new levels. And should we take them seriously or not? When Vicky and Katkowski found these solutions 70 years ago already, some people say that this is simply some unknown to us defect of Bissell-Pitt equation. Other people took them seriously, and so all this solution disappear in non-relativistic limit, and I will show how they disappear. This is just coupling constant as a function of speed of light. How we can go to non-relativistic limit? We should take small momenta, or small relative to what? Relative to masses. And why relativity appears at all? Because we have finite speed of light. Therefore, formally, we can introduce speed of light as a parameter, not take into one, and increase speed of light. And if the effect disappears, this means that we go to non-relativistic limit. And if it doesn't disappear, this means that it is a purely relativistic effect. And so on the left panel, this line corresponds to non-relativistic solution for coupling constant alpha. So for given binding energy, we have coupling constant alpha. Of course, it doesn't depend on speed of light because it is Schrödinger equation. And green curve is solution, normal solution for coupling constant alpha, and speed of light increases. It tends to non-relativistic value. So this is normal solution. And on the right panel, this is again coupling constant alpha, but for abnormal solution as a function of speed of light, it increases up to infinity when speed of light increases up to infinity. This means that abnormal level pushed out from the spectrum. Therefore, to keep them for given binding energy, we should increase coupling constant up to infinity. And if this just means that they disappear in non-relativistic limit. In non-relativistic limit, we should increase up to infinity coupling constant in order to keep this abnormal states. So nothing for Schrödinger equation, but this is very interesting property of the bit-salpeter equation. And so in our paper, we calculated the Fock calculated the contribution of two-body Fock components of in this system, and we found that for normal states, this Fock two-body charged particles and small admixture of smaller of massless particles. This is the content of the normal states, but on the contrary, for the abnormal system, we found that they consist almost for 100% from exchange particles, from photons, and only a small admixture of massive charged particles, which create this system. And so all that put on agenda experimental detection of these abnormal states. Of course, how to find them? It would be ideal to deal with nucleus, anti-nucleus, because they have equal masses, and the charge Z equals to 11, natrium anti-natrium is already enough to have enough strong field to create these abnormal states. But unfortunately, they are not available. We have them in our disposal. Only anti-helium-4 was created in the laboratory. Therefore, we should deal with electron and heavy ion. What does it mean? These abnormal states are created in strong field. Therefore, charge should be larger than alpha over alpha equal pi over 4 corresponds to Z larger than 107. And therefore, constituents masses should be very different. We have heavy ion and electron. Therefore, we should generalize this approach for the case of very different masses of constituents. And therefore, first equation, do they still exist, these abnormal states, if masses are very different? This is a bit-salpeter equation for equal masses first. It was solved by Wick and Katkowski by following way. They represent this bit-salpeter function in integral form, substitute it in initial bit-salpeter equation, and find equation for this function which enters in the integral. And just from here, we can clearly see the origin of this abnormal states, because this was written from principal quantum number equal to 1, but similar equation exists for any. And you see, this is homogeneous equation, and usually homogeneous equation, like any Schrödinger equation, they have an infinite spectrum. So for given quantum number, even for ground states relative to number n, we have infinite series of solutions. This is just all these solutions corresponds to abnormal states. So this is mathematical origin of abnormal states. It is clearly seen that we should have not only normal states corresponding to different principal quantum numbers, but also series of abnormal states. Now consider the same for non-equal masses. This bit-salpeter equation for non-equal masses, and delta is ratio of difference masses over sum of masses, or R is simply ratio of one masses to other masses, say heavy ion masses to electron masses. For heavy ion, it's a huge value, 10 to 5 degree, because mass of proton in 180 times larger than mass of electron, then you can have 100 protons. So you have this huge number for R. So mass is not only unequal, they are very, very unequal. R can be considered as infinite number even in this case. And the method is the same with Salpeter equation wave function, also represented in integral form now with non-zero delta because of masses are non-zero. Again, one can obtain differential equation for this function, and it gives us spectrum for any delta now. It is solved very, very easily and quickly by Mathematica, simply instantaneously, and the solution can be found numerically. But the better, it was trick by Kutkowski, one can relate this solution for unequal masses with solutions with equal masses by this substitution of arguments and the factors, and also eigenvalue for unequal masses is related to eigenvalue with equal masses also. This was found by Kutkowski. So this allows us to solve unequal mass problem even almost analytically. We can solve equation for equal masses and then extract from here dependence for unequal masses analytically. And what we have as a result, I give simply example of this function G as a function of Z. This is a solution for equal masses. It's symmetric relative to invariable G. And this is for unequal masses, for ratio equals to 10. It is somehow distorted. So it can be obtained, I repeat, numerically solving the equation for unequal masses or analytically taking the relation between the equal and unequal masses. And similarly for abnormal solution for kappa equals to 2. This is equal masses solution, but abnormal. And this is unequal masses solution, also abnormal. It is shifted to the left, but the form is more or less the same. And I emphasize that abnormal solution as a function of this variable z always has nodes, zeros. If there is no node, solution is normal, as has been shown at previous slide. If you have node, solution is abnormal. This is peculiarity of the abnormal solutions. Go further. Now, having a relation between unequal and equal eigenvalues and expressing this eta, I show you again. I'm sorry. Eta is the ratio of total mass divided by eta for masses in the equal case squared, or for half of sum of masses in the equal case. So we can find m mass and then binding energy. And so doing that, I'm sorry, excuse me. Doing that, we can obtain analytical relation between binding energy in the case of unequal masses with binding energy for equal masses. It has this form for ratio of masses, if ratio of masses tends to infinity, and this term, ratio of binding energy with mass, is negligible. Therefore, in this limit, we have that binding energy of for unequal constituent masses is 2 times larger than binding energy for equal masses. So effect of different masses is attractive, and what we get if we will have bound system of heavy ion and electron, we will have that the binding energy is 2 times larger than binding energy in the system of electron and positron. So it is good because it simplifies somehow observation of the states, because body energy are very small and therefore experiment could be very complicated. Then now let us again check the content of this abnormal states in the case of different constituent masses. So the our2 for that will be beta function. Of course, beta it contains state vector, and state vector contains a set of components. And the best way, in principle, to solve eigenstate equation for the state vector and see which how much each for component contributes. But in practice, it is very difficult. This works are presented, will be presented in at this conference. I saw, for example, talk by Simba corresponding to positronium for large coupling constant. But we go in different way. We solve this equation. We find this beta function. And after that, from this beta function, we extract only two-body contribution. We are unable to extract everything. So we will calculate two-body for components, and after that, calculate two-body contribution to the normalization. How we do that? We have beta amplitude, and at the quantization plane, for example, for equal time approach, with this very complicated Heisenberg operators become simple Schrödinger operators. Therefore, this matrix elements contains only two-body for components, because we have two products of two operators. All other matrix elements give 0. And the same for the light front quantization. If we consider light front approach, then if you will take beta function on the light front surface, I work here in the explicitly covariant approach when light front surface is given not by equation t plus z equals to 0, but omega x equals to 0 and omega squared is 0. But it is a technical detail. And so if we take beta amplitude in coordinate space on the light front, this means that it can be shown easily that this means that we should, in momentum space, we should integrate over light front variable k minus in usual case, and it gives us relation between beta amplitude in momentum space and two-body Fock component. And since this beta amplitude in any space, in the coordinate in momentum space is known, it has been found from the equation, we can find psi two-body wave function. This is the relation between two-body wave function and this function which determines beta amplitude via integral. And this function is known. It is expressed through equal mass solution, as I've already shown. So two-body contribution is given by this integral. We substitute here this expression for wave function, then express this solution for equal mass solution. All the dependence on mass appears in all these factors. It can be analyzed, and in asymptotic, it gives the factor R in fourth degree. R, I remind, ratio of masses, divided by total by total normalization of full state vector, which also depends on R. Now we find this in total. So one can show that
normalization condition for the state vector is equivalent to normalization condition for the electromagnetic form factor. So in practice, we calculate electromagnetic form factors, and then require that it is 1, and it gives us normalization of the state vector, so the total factor in this state vector, and in this way we find n total. Okay, good. We find n total, and it turns out that it also at large R has the factor R in 4th degree. So in the formula which we had, so in this formula we have R in 4th degree, and total is L sign contains R in 4th degree. So for large ratio of the masses, heavy ion and electron, we have finite limit for N2. And it turns out, even surprisingly for me, that this total, this limit is almost the same as for equal masses. So this is the numerical results. The first three numbers corresponds to normal states, kappa equals to 0, and different ratio for masses of heavy ion and electron. 1 is binding energy for some parameters. This is contribution of two-body sector in normal states. Not 1, but 65%. Then we increase the ratio, binding energy increases, as I told, and N is very stable. Higher digits, of course, change, but we have the same contribution of two-body state in the normal solution. Then R tends to infinity, binding energy increases exactly 2 times, as has been shown analytically, and N is still stable within 2 digits. Consider now abnormal states with corresponding kappa equals to 2. And again, the ratio of mass is 1, 10, and infinity. Binding energy increases 2 times, and contribution of two-body sector in full state vector is very stable. It is about 1%. So the system consists on 29% consists of photons, still in the case of different masses. And at last, the case of kappa equals to 4. Kappa, it is, I remind you, the quantum number which characterizes the abnormal solution. And in this case, binding energy again increases, as should be, by 4 times. And contributions of two-body components is still stable, and now it is a little bit less than 2 times less than 1%. So the conclusions that abnormal state survive exist. This conclusion survives in the case of different constituent masses, which is practical case for experimental study of these solutions. So my conclusion that the effect of unequal masses is attractive. Binding energy increases when the ratio of masses increases. When this ratio tends to infinity, it increases by factor 2. Two-body constituents contributions N2 changes insignificantly and remains small for abnormal states, and abnormal states with unequal masses are still dominated by massless exchanges. And remarks, the abnormal states appear due to strong Coulomb forces. Therefore, spin effects can change these forces, but what we know, if spin are parallel, the interaction less stronger. If spin are anti-parallel, the interaction more stronger. So nothing dramatic happens.
it cannot change significantly our conclusions. Another remark, we should have strong electric field, alpha more than, not alpha, Coulomb constant more than pi over 4. This means that Z must be more than 107. On the other hand, we know that the charge larger than 137 cannot exist, because what happens if you have opportunity somehow increase the charge, and if it exceeds 137, in this strong electric field, a pair of electron positron is created. Positron is absorbed by this charge. I'll finish now. Electron goes to infinity, and we still obtain charge 137. But it is for point-like system. If the system is not point-like, but like nucleus, it has been calculated this maximum charge is 170 for fine size of nucleus. Therefore, the domain of charges corresponding where we can have abnormal systems is from 107 to 170. I don't know whether the nuclei with so high charge exists. I don't believe, but maybe they exist. But transuranic nuclei with charge larger than 107 are created in laboratory. They're not very long line, but enough for experiment, I believe. For example, there is element called fluorium. It has charge 140 and life of time 2 seconds. Maybe 2 seconds, I think that is enough for experiment of this kind. So it would be very interesting, but not easy to study this problem in experiment, to detect the abnormal state. This is the same problem which has been solved from the beginning of quantum mechanics, when the founders of quantum mechanics predicted Coulombian spectrum. It was confirmed. So now this is the same problem, but in relativistic region for strong field. And electron-ion collider may be a good tool for this search. But we don't need high energy, we need heavy ions. But we need small energy in this study because we consider spectrum of the system. So I think that it would be interesting to pay attention on this problem and try to think how to find this, how detect these states in experiment. Thank you very much for your attention.
Thank you, Vladimir.
Yeah, so this anomalous state exists in a large coupling. So
the setting is large coupling, right?
So I wonder, theoretically, at least, all these beyond the ladder approximations, like cross ladders and or higher topological non-planar contributions will be important in the large coupling. So
large coupling,
right? So it's not clear.
Yes, this is
could be just.
I agree. One can say that for large coupling there is no Coulomb field, Coulomb interaction at all, because interaction changes itself when it is very strong.
Yes, of course.
So I don't know. Yes,
will play the role. So I think in the large coupling, I think one has to really look at the high order,
better fall to solve full field theory.
Yeah. So can I ask you, in the numerical result, I think you indicate you have tried.
Yes, Shaun already told that cross ladder does not eliminate that. Yes.
Can you tell that how these numerical results have changed by adding those?
By adding?
Yeah, by adding these cross diagrams, etc.
Well, it increases the binding energy always when you add the cross line.
So in this sense, it goes in good direction.
Yes.
That means that polarization goes down.
The problem that
yes,
if field becomes weaker, of course, this could disappear, but it does not become weaker.
So Dr. Kamanov, you mentioned the electron ion collider is a tool for this search for this let's say abnormal states. So what is the how to detail, let's say, process in your mind, how to use the electron ion collider to search the abnormal states?
We should have heavy ions.
Right.
But of course, I already told that we don't need high energy, we need small energy.
Okay. So then what kind of process, what kind of observable you have in mind to?
I think that the same as studied when the spectrum of hydrogen atom was studied. We should see spectrum and then transition between different levels and see that we will find new transitions, new levels.
But the electron ion collider, the target is the nucleon or nuclei, right? So basically, electron shoot on this let's say nucleon or nuclei. So what kind of how do you get this spectrum for the abnormal states? So what kind of process?
There is no difference between normal and abnormal states in this respect.
Can I make a comment?
Sure.
Yes,
because I maybe have an idea how to do that. Was it technically possible is a different question. So what you would do is you have the virtual photon interacting with the nucleus. You excite it, and then actually what you detect is, for example, photons which come out of the different excitation states. And if you have abnormal ones, and they would be, the photon energies would be different than what you would get by normal excitation of a gold nucleus, which is already kind of, we have models for. It's very difficult to detect these photons because normally they are in an MEV range, go down the beamline and you have to filter them out. We are integrating some detection mechanism for this type of photons, but whether you can really realistically do that with a beam background in the is very difficult.
So it's basically like detecting a heavy photon.
It's not a heavy photon, it's just a photon.
Just a photon.
You are making up some, it's not beyond standard model type of heavy photons would be something different. So this is just a special state which has a different excitation. Kind of, it's at least my understanding.
But how can it be reflected in the photon as a spectrum?
Because if you have different excitation energies, you get different photon energies.
Okay.
As simple as that. But I have a question to you, if I may. Yes. I just use that I have the mic. Why don't you look for something if you say you need heavy ions? Why is the beam energy scan, which has a star done with the lower beam energies and heavy ions, not the best way to look for this?
Not heavy ion, please repeat.
So you know the star experiment at RIC? Which is star experiment at RIC, the RIC facility, which is heavy ion on heavy ion. We have just done a beam energy.
Heavy ion by heavy ion?
Yes.
But they should have opposite charges. No, I don't.
Opposite charges.
You
said you want heavy ions to produce this.
Heavy ion and electron to have bound system.
Yes.
And produce the states, yes. But what do you propose to?
No, then it's okay. Fine. I misunderstood what you were saying.
Okay, thank you.
Okay. So
but I would like to emphasize again that in principle, the methodology is the same. We should study the spectrum of this system. But now we should study the spectrum of highly excited states and see deviation from the Coulomb's spectrum.
Two questions. One, you see that when the mass are different, the system becomes more bound. But
by two times.
If you introduce mu, the mass of the change particle, how it will evolve? It will be also in favor larger mu's?
I don't know for non
or non-zero
non-zero mu. It has not been studied. But one thing
you cannot feel how it will evolve.
I think that we should think about that and see. But I think that it can be understood qualitatively even.
Yes, but qualitatively should give larger value of mu.
Larger value of mu for given coupling constant means small binding energy because the potential well becomes more narrow and energy goes to up. That's all that can be.
And the second one is, I think this, if you go to this electron-ion collider, the problem is the energy. They are talking about 140 GeV or TeV.
Yes, I say.
I would rather be tempted to put on a penning trap, which is zero energy.
Yes.
You take ions and you put electrons at zero energy, and then you can produce this.
Interesting, yes, but where will you take so heavy ion?
Well, you take it from somewhere.
Okay, from somewhere.
But you put it on a penning trap. It's practically a red.
Yes, I agree, absolutely, yes.
And then you can also put whatever.
But the problem to have them, we cannot have anti-nuclei. That's why we work with heavy
ions. You
ions.
can have it in dissolved. You can have heavy.
Because to have heavy ions, one should start with not ions and remove the electrons from it.
Anyway, we are not experimenting.
Okay, so we have the last question here. The last question. Tobias, just a moment.
It's just a clarification. I'm confused. Is the system of states you are looking at from the atomic system with the heavy Z? In other words, you know, it's a spectrum that's atomic, or are you looking at the nuclear spectrum of the heavy ion?
No, atomic.
Okay. So the discussion then becomes a totally different.
Okay.
Okay, thanks a lot, everybody. Thanks a lot, Vladimir and Xiaomei, for the talk. Yeah, we need Bruna de Oliveira, Emanuel Oliveira, Leonardo Santos, Bianca Oliveira e a Arlene e Cristina para falar com a secretaria do INCT. So thanks, everybody. We go for coffee break and then we convene at 4:10. Okay, see you.
Not yet turned on, right?
Right. No, it's not.
Testing, testing. No?
No. Why it's not?
É
para testar como ligar aqui.
Yep.
Hold it down.
Just hold it down.
Okay.
Yeah, it's working.
All right.
So it's 1 hour 20.
Let me test to see if my students can hear. Weiji, can you hear me? Maybe he doesn't have his microphone on.
I think we can hear you, but the voice is a bit
Can you hear me,
low.
Weiji?
Yep, yep. But I mean, it's only by my laptop. I mean, we cannot get access
don't
to
hear
the
him.
speaker in the classroom.
Is there need? Do you need to activate something here to hear somebody who's online who's asking a question? I see Luke. Luke has a hand raised.
Yes, maybe. Maybe. Let me ask him.
Hold on just a second. Testing things here.
Tudo bem? Se alguém. James, test again.
Test again. Okay. Weiji, you want to say something and see if we can hear you this time?
Que ele queria que alguém está online.
Huh? This is the student. This is the class in Iowa.
Entendi.
I see a hand. I see someone has their hand raised here. You want to? How do you recognize somebody who's got a hand raised? Yeah. I don't know.
Yeah. But I saw that John was following.
Who?
John.
Yeah. He sent me an email. Yeah.
I was surprised.
Yeah.
He said that he allowed it.
Huh?
He said that he allowed it.
Okay.
But
So-
I don't know why.
So maybe Weiji, could you try again? We saw you turned your microphone on.
Yeah, I'm trying to solve the audio issue here.
Okay. Trying to solve other issues. Okay.
Okay. So he, you can hear me.
Now he's
Yeah, we can hear him. Yes. Huh?
Our class is there.
Yes, another issue. Have you succeeded in hooking up the projection system?
Yes, we can see the slides now, but the sound is really low.
Sound is very low. That's
Yeah.
what we're in because the sound here is plenty loud. Try to turn it up on your laptop or probably your
Yeah, I did.
students come to the front of the class to be around the laptop so they can hear.
You can hear the voice. I'm playing something weird here, but I don't know why the sound of the Zoom is so low.
Try your laptop sound. See if that's turned all the way up. And also Zoom sound if you have a Zoom control.
Where is the Zoom sound? Do you know where the Zoom sound?
Oh, yeah.
switch to phone audio. Can you speak again, Professor Berry?
Yeah, see, how does this sound now?
Oh, good, good, good. All good.
We're okay? Okay.
Yep.
Turn off his mic.
Okay, you can turn off your sound and, okay, great, thanks.
Okay, good afternoon. Now we have a lecture of Professor James Berry. Professor, thank you.
Thank you very much. So welcome to a new experiment for Light-Cone conference series. It so happened that I'm actually giving a course at the present time, Physics 526. So welcome to lecture number 12. You all will recall that we have in the recent few lectures covered the, among other things, the standard model in brief. QCD is part of the standard model. And we've also been discussing the quark model and Lorentz transformations and a host of background material. And the timing worked out pretty well for this opportunity here at this international meeting, of which this is approximately the 35th, 36th meeting in a series. And I've had the good fortune to attend about 30 of them. So it's a great pleasure to be back here again in Rio de Janeiro. My second visit, my wife and my second visit to Rio, our third or fourth visit to Brazil. Anyway, this is a great opportunity. With the kind agreement of the organizers, this will be in part a little bit more pedagogical for the benefit of the students. And then we'll start ramping things up and covering in fairly rapid fashion some recent developments, which are more or less are basically highlights of talks that are going to be given in the remainder of the conference here. About 8 of them, in fact, touch upon applications of the framework that we'll be talking about today. So by way of doing 2 things simultaneously, the formal talk, the formal title for the conference talk is Basis Light Quantization, Foundations, Recent Results, and Plans. And for the benefit of the students and to put a bit of a context to what we're doing here today, it's helpful to stand back just a little bit and take a look at what we could say is a kind of general starting point, which is our QCD Lagrangian. And we're looking to solve this for making predictions to compare with experiment. And some of the most standard tools that we learn about, certainly in our coursework, is how to do Feynman covariant perturbation theory. However, we're more ambitious these days. We favor trying to do things non-perturbatively. And so if we take a quick look at the landscape of opportunities here, we'll immediately notice that lattice gauge theory is a covariant framework for solving QCD non-perturbatively and predicting quantities of interest to experiment. Over here, and we've heard some talks today already, another approach would be your covariant wave equations approach, going back to Beta and Salpeter, Dyson and Schwinger, and subsequent works creating more variations on the theme of covariant wave equations. And this is great for solving non-perturbative bound state problems up to certainly 2 degrees of freedom and 3 degrees of freedom, but begins to bog down when you want to go to, say, 3 or more dynamical fields in the problem as active fields. So we'll switch over here and be talking mostly about Hamiltonian field theory, which is a branch of non-perturbative physics, also emerging from lattice gauge theory. If you're into
equal time quantization, what we call equal time quantization. But for our purposes, we're going to look at this as a light front Hamiltonian approach. And I'll spend a little bit of time reminding ourselves of some of the particulars for how you would set up such a calculational framework in the beginning. And it's at first we can be very general. We want to take your Lagrangian, do your Legendre transformation to come up with your energy momentum tensor. And from there, the next step is to actually select your coordinate system. And for most of what I'll be talking about today, that's going to be the light front coordinates. And inside that choice, we then identify the generators of our relativistic theory. And we'll do a little bit of the details of this in a little bit. Since we're talking about QCD, we have a gauge theory. The next choice we probably should make is to how to fix your gauge. And the popular by far choice is to fix the gauge by taking one of the components of the gauge field and setting it to 0, the so-called A+ component. Then we go down through a series of steps, and we'll see this in a little bit of more detail, but just to give you the headlines for this, you want to eliminate your dependent fields using your equations of motion. And in the light front field theory, this converts our fermion-Dirac fields into Pauli fields. And this is the origin of the statement that you often hear people make, that at the end, you end up with a Hamiltonian framework that looks a lot like a non-relativistic quantum many-body problem, except that you can create and destroy particles along the way. So one of the attractive things about this approach for our applications is that there's a lot of established techniques that allow us to take advantage of the fact that once you get everything in terms of fermions, which are Pauli fields, basically two-component fields, those are looking a lot like non-relativistic fermions as far as spin space is concerned. And the framework that we'll be talking about here is to go further. We propose to set up this problem as a Hamiltonian eigenvalue problem in a particular basis space, which will be selected for the QCD type applications we have in mind. And that is going to be primarily, initially, bound state problems. So let's take our modes, if you like, to be those of convenient choices. For the transverse motion, we're going to take a two-dimensional harmonic oscillator. And for the longitudinal, the third spatial component, we're either going to be using Jacobi polynomials, or we'll revert to a momentum space framework called discretized Light-Cone quantization, established by Pauli and Brodsky many years ago, and pick periodic or anti-periodic boundary conditions. So one of those two choices will appear in the applications that we have coming forward here. Next, you want to quantize the theory. So within these chosen, if you like, modes, your basis now becomes a set of quantum modes. So your fermions and your bosons are going to occupy modes of this reference system defined by these basis states. And this leads us to field expansions and hence developing everything in terms of second quantized language under the label basis light front quantization. To be practical and proceed from there, you have to make the problem calculable. And so you have to select some sort of cutoffs to make your infinite matrix problems finite dimensional and therefore solvable with advanced techniques on modern computers. And the labels here, which we'll come back to, are just listed for convenience, and we'll come back to each of these in a little more detail. Computationally, you're now in a position to calculate your Hamiltonian matrix for your system of interest, be it meson, baryons, nuclei, whatever you want, as a quantized relativistic many-body field theory in Hamiltonian framework. So you can calculate, in principle, the Hamiltonian matrix and store it. It very quickly gets to be a large sparse matrix eigenvalue problem, and high-performance computers today, with our technology to solve quantum many-body problems, is an ideal match. Framework matches computational capabilities at the leading edge of computational physics, at the leading edge of what can be done with high-performance computers. So the next step, you're on a high-performance computer, you actually solve the mass spectrum and obtain the eigenfunctions, which are called the light front wave functions, called the eigenpair problem. And then you store those, again, using high-performance computers. And from there, you can now begin to relate to your favorite experiment, be it lepton nucleus, lepton hadron, hadron-hadron scattering experiments using the standard setup, which is operator sandwiched between some initial state and some final state. That's your transition amplitude. And from there, cross sections and any other observable, in principle, transition rates, static moments, and so forth, should be in principle calculable. So that is an overview. And what follows now is to go back and see a few more details and then go into some current and planned applications. Interrupt me at any time if you have questions, and I'll be happy to answer them. Okay, so in a nutshell, we have from the work of Dirac, going back to 1949, as has already been mentioned by others, basically three forms of relativistic dynamics that we can freely adopt. And the textbook version of this is relativistic dynamics in what would be called the instant form, where we have the light cone, and we have the two transverse directions pictured here on a plane. That's the best we can do with pictures. The system is defined to evolve in time, which is the zeroth component of the standard 4-vector. And this framework, the Hamiltonian, is adopted as the energy component, the zeroth component of your 4-vector. That's where your dynamics begins. You have your kinematical operators, your momentum and your angular momentum, your 3 momentum, your angular momentum, and 3 dynamical generators, one of which is already mentioned, the Hamiltonian, and 2 others, and your familiar relativistic energy momentum dispersion relationship. So that's the textbook version. We come over here to the light front form, and here we make a transformation to light front time, defined as the linear combination of x0 and x3. And for us, the system, therefore, has a time-like direction that proceeds perpendicular to a different plane, pictured here. Your x-perp plane is still your xy. It's an xy plane, x-perp, and your linear time vector is going off in the diagonal here. So in this setup of coordinates, which is not related by a unitary transformation from this set of coordinates, Dirac showed that you have your choice could be a Hamiltonian, which is P minus, defined as P0 minus P3. And if you make this choice, you end up with these seven kinematic generators. There's no interaction dependence here. And these are the ones that we pay attention to when we talk about the symmetries of our solutions for our systems of interest. So dynamically, we have sorry, I said over here we had 4 dynamical, three vector components and P naught. Here we have 2 vector components along with the Hamiltonian P minus. We also have the dispersion relationship, which is often commented here, looks a lot like the dispersion relationship of non-relativistic quantum mechanics. If you imagine that this denominator is just like a mass itself, this is just like p perp squared over some mass. So it's like the non-relativistic form of kinetic energy. And there's a big advantage here in terms of the types of matrix elements and quantities of the many-body problem that emerge from that. And not to forget, there's the also the third form of Dirac's relativistic dynamics called the point form, but we're not going to be talking about that. Okay, so given that, we can say you start with the QCD Lagrangian, you follow through the steps we mentioned, you identify those 10 generators, you select your Hamiltonian generator, and then you go through the process of for gauge theory, fixing the gauge, and then using your resulting equations of motion to reduce the problem to this form that looks like a non-relativistic quantum many-body problem with creation and destruction of particles being allowed. At that point, you can ask, well, just how complicated have we gotten? What does QCD look like when you get to that stage? And the answer is, well, first look at QED. If you do that entire process for QED, you still have fermions that absorb photons and emit photons. By pictures here are meant to mean all time orderings. You have 2 terms that are picked up from fixing the gauge, which are instantaneous interactions of higher order in the couplings. This is an instantaneous fermion exchange and an instantaneous gluon exchange between in this case, a fermion and a gluon, in this case, between 2 fermions. So, but basically you just have 3 terms taking care of all the non-trivial physics of QED. So that's, on the one hand, deceptively simple. You say, you know, I'm a low energy nuclear physicist by training, and my Hamiltonians typically have 20, 30 constants and 50 to 100 terms. So, you know, I'm used to seeing tremendous complexity, and some of you are too, because you work in that area as well. So this looks really, really appealing. Now, upgrade your gauge theory to QCD, and you pick up additional terms coming from the gluon self-couplings. The famous triple and quartic gluon coupling terms emerge. These second order in the field, and again, you have additional instantaneous, so-called instantaneous terms coming from the gauge fixing, the elimination of unnecessary degrees of freedom, if you like. So there's a fermion gluon and a gluon coupling term that emerge. But no, nevertheless, there's only these 4 in addition to these 3 for QCD. So again, it's in a way deceptively simple. You say, that's all I have to worry about. Question? Is there a question? You go? It's okay? It's deceptively simple. Okay. But as we say in English, the devil is in the details. And you actually heard talks earlier today about some of the hand wringing that we do over implied assumptions, absolutely, when you set the problem up like this. Okay, there's implicit assumptions being made, which have been much discussed in the earlier talks. Okay, so now what happened in 1985 was Pauli and Brodsky. Hans Christian Pauli was also a non-relativistic nuclear many-body theorist, teamed up with Stan, who's very well known in light front field theory term, and they did some of the first setups in momentum space. They just said, let's take these Hamiltonians, both QED and QCD, set them up in momentum space. So the transverse direction was X and Y momentum spaces with periodic or anti-periodic boundary conditions. The other direction, the X minus direction, X super 0 minus X super 3, was taken to be also a plane wave basis with chosen boundary conditions, and then just set the Hamiltonian up and try to diagonalize it in momentum space. And I once remember Hans Christian Pauli telling me, I was a visitor to Heidelberg at that time, if I have to go beyond 1,000 by 1,000 matrix, I'm going to give up. He thought all the physics would emerge in a matrix as small as 1,000 by 1,000. Well, unfortunately, that didn't work for him, and it doesn't work for us. And maybe someday there will be some, genius breakthrough to show how to make this all work in a small basin. Now, that's why we're using high performance computers these days. Okay, so some years later, we invented, and this was about 9 co-authors involved here, including Stan and others. We said, well, let's generalize momentum space to an arbitrary space of functions. So momentum space can be thought of as plane wave functions. Well, let's take the plane waves and put them aside and say, we're trying to solve QCD here. Plane wave basis doesn't really sound too good for solving bound state problems. Well, let's put in a better basis. Or make it first generic. Let's just say, look, we can quantize a theory in any set of modes we want, provided we obey certain mathematical conditions. The modes should be, for sake of convenience, should be orthonormal and complete. And in our coordinate system, viewed in momentum space, you have certain delta functions or Kronecker deltas that you would want those functions to satisfy. So that's it. If you talk about basis light front quantization and the freedoms available, you could have, some favorite choice of functions that you like to use that satisfy these conditions, and maybe they'll be having some advantages. Our choice from the beginning has been, on the one hand, to take, for the transverse modes, we're going to take two-dimensional harmonic oscillators, which have harmony with ATS QCD, which was coming along at about the same time. But harmonic oscillators are favored in non-relativistic quantum many-body problems for certain analytic and numerical properties, which I'll have a chance to mention in a little bit. In particular, symmetries and controlling symmetries, making your basis space as complete in the description of the symmetries that you're expecting to emerge based on just looking at your Hamiltonian. I know what my Hamiltonian commutes with. I want my basis space to respect as many of those symmetries as I can. I can do that if I make a harmonic oscillator or a plane wave choice. And basically, these are the only two choices that seem to satisfy the nice analytic closed form expressions that we desire to have to make our truncations less severe. Symmetries, when you impose them, mean you don't have to make an additional truncation along the way, as it turns out. Okay. So besides the two-dimensional degree of freedom, the transverse motion, the x-perp coordinate, which happens to be linked to the longitudinal coordinate, will make a product with a separate function for the longitudinal motion. That's the Jacobi coordinate or DLCQ choice that I was referring to earlier, either plane wave or something else. So that's it. That's where we set things up at first, and we did a number of initial studies and convinced ourselves this looked promising. Okay, so let's talk about symmetries. How many symmetries can we impose in our basis space? and save ourselves work? Well, first of all, we can construct many parton basis states. Now, when I say many parton, I'm using a language which I'm going to apply to QED as well as to QCD. I'm going to fix fermion number when I talk about QED. I'll fix baryon number and charge when I talk about QCD. Fix it. The basis states of only one baryon number and or one charge will be involved at one time. We're going to fix the basis to have total angular momentum projection fixed. So all my partons will have orbital momentum. They'll have orbital angular momentum projection and spin, and that's going to couple up to total angular momentum projection, which is J sub Z. And we're going to sum over all partons in every single part, in every many body basis state, and require that have the same J sub Z. So for fermions, it could be a 1/2 or 3/2 or 5/2, or a boson, it would be a composite system of a boson, it would be 0, 1, 2, 3. And the advantage is, I'm just going to give you a heads up here. When you make your many body basis space like this, you carry out a single Hamiltonian eigenpair calculation, you actually get all solutions or access to all solutions with total angular momentum greater than or equal to that minimum value that you chose. And this turned out to have numerous advantages. Okay, we want our basis to conserve total longitudinal momentum, the so-called Bjorkane sum rule. So the basis spaces we work with have the sum over longitudinal light front momentum fractions of each parton equal to 1. That's natural and easy to do with the basis we work with. If we're working with the Jacobi coordinates, we'll introduce an additional cutoff in the number of such modes in the longitudinal direction. And similarly, we're going to introduce a cutoff in the total number of transverse modes. And that cutoff is the sum over all partons in every many body basis state, twice the radial 2D radial quantum number plus the magnitude of the orbital angular momentum projection plus 1 is less than or equal to some number I'll fix, n max. And backing up to just a moment up here, if I'm working in the DLCQ with discretized Light-Cone quantization framework, I'm cutting off my modes in the momentum space as well, with the total sum over all modes has to be less than or equal to, sorry, it has to actually equal exactly total K, because that's a conserved quantity. So there's 3 regulators to watch. In practice, only 2 of these appear in any given calculation. You'll have always n max, and you'll have either K or L, not both. So that's the kind of basis spaces that are set up, modes, if you like. What kind of modes I'm going to let my partons occupy. I can also work with what are called the internal coordinates of the system, which are guaranteed if I sum over all partons that the total transverse momentum vectors are equal to 0. Working in momentum space, I can insist on that quantity. That's a DLCQ type condition. We'll see in a little bit the harmonic oscillator problem and how that works. Then, since I'm going to be talking about many body problems, I'm actually going to prefer to work in what's called a single parton representation. Every field, every parton occupies its own mode, and it's independent except for these global symmetry constraints from what the other partons are occupying. And it obeys the various, like Pauli exclusion principle is also built in from the start. And because of this, I've overcounted the number of degrees of freedom if I'm only interested in internal motion. And I can correct for that for the harmonic oscillator problem by introducing a Lagrange multiplier term, a positive coefficient lambda times an operator that acts on the total center of mass of my system. And for being positive, it'll shift all states of excited center of mass motion away from the physical states of interest. And that way I isolate the physical states, which will all be in an eigenstate of center of mass motion, which I can separately divide out of my solution. That's the beauty of the harmonic oscillator picture. If you look carefully at momentum space, working in a single particle representation, it'd be the same thing. You just, in that case, subtract out the center of mass motion. You don't have to do a Lagrange multiplier. Our many parton problems are solved as global color singlets. That's a restriction we'll put in. We'll assume the symmetry is that we only solve for global color singlets. I've already mentioned light front gauge. And then to make the problem tractable, we also will not include all possible Fock spaces. I don't include all possible quark-antiquark pairs or all possible gluons in my basis. We'll typically truncate that at some level. And then we have to talk about consequences of that. Very good. Okay. Now, not to skip, but only to go over very, very briefly what goes on with regularization and renormalization approaches. Many years ago, people would throw up their hands and say, "Oh, we don't know how to renormalize a non-perturbative calculation." Well, a lot of progress has been made in the meantime, and there are a number of schemes that have been introduced to address these issues. Aside from the ordinary introduction of counter terms, there's a sector-dependent renormalization, and here are some of the key references, some of the early key references, a lot more references in the meantime. Another one that's been introduced, and we'll hear more about during this meeting, is the Renormalization Group Project for Effective Particles, or GPEP. And there's a couple other techniques from many-body theory available that have not yet been adapted to the BLFQ problem, but look like they're promising and could be. So again, and there are talks coming up here which address one or more, actually more than one of these schemes. So that pretty much gets us set up for what we want to do. And the next step in the process is to begin to do some work. And let us remind ourselves of what is the workload looking like going forward. Well, what do we want? A hadron, or any composite system we want, could be and will be positronium in some of our problems, is viewed as a superposition of many parton basis states, where every parton has some coordinates in the problem, and it's a set of partons, and little n represents a so-called Fock space label. So if I have a QQ bar system, that might be my first Fock space, and there'll be an amplitude, the so-called light front wave function, for it's a function of all the variables those partons can have in that Fock sector, and we sum over all Fock sector. So a positronium would be E plus E minus is the first Fock sector, and then maybe we'll turn on a photon. So next Fock sector would be E plus E minus and one dynamical photon, and so on up the ladder. Add everything you can that conserves the basic quantum numbers of positronium. That would be the endpoint scheme. Similarly for mesons, and by simple extension for baryons. So again, just a reminder of some of our variables. We want to eventually get the light front wave functions from the Hamiltonian eigenpair problem, and from them calculate matrix elements of interest, such as parton distribution functions, form factors, and so forth. And Stan Brodsky's favorite saying is that in this thinking, hadron physics without light front wave functions is like biology without DNA. All the information you want is in principle available in your light front wave functions. And then your choice of operators that connect you between that information and a given experimental observable that you're interested in evaluating. And it's already been mentioned here, we have a whole family of observables, starting with generalized transverse momentum distribution functions, which characterize the properties of our composite systems. And by doing selective integrations, you tie yourself into other observables all the way down to having just a single number, some conserved charge at the end of the day. But different selected integrations bring you from this information, which is essentially products of wave functions, just generalized products of wave functions with different arguments. And then you do the integrations necessary to get you, for example, to form factors or generalized parton distributions and so on. So that's why we want these light front wave functions. Okay, so one of the first test cases which we did was positronium itself. Why? Well, on the one hand, the gauge theory is simpler, fewer processes, no gauge self-couplings to worry about. On the other hand, it's a very well-known, well-studied system with other methods. So how does it look when you do this on the light front? Can you get the ground state properties of and low-lying properties of positronium as a light front Hamiltonian eigenvalue problem from QED? So the very first problem was done. We're going to do this harmonic oscillator basis, which is not a very good basis for atomic physics. As you all know, atomic wave functions have very long range tails, not anything like harmonic oscillator. So this is a numerically challenging problem and very hard to do with the chosen degrees of elements that we want to bring into the QCD problem. But nevertheless, let's show we can do it. We can hit it hard enough with computational power to converge it. So we'll start with a stronger coupling than the perturbative coupling. It's not 1/137. So the initial application was to do this problem in a limited Fock space, just electron-positron pair, and a perturbatively calculated one photon exchange interaction. So this has the look and feel of a relativistic version of a Schrödinger equation, where the one photon exchange interaction carries all the dynamics, and you diagonalize this Hamiltonian in the chosen basis, you should get all the spectroscopy of positronium in principle. Numerical challenges, yes, as I mentioned. So we have to work initially with some finite photon mass to regulate the infrared properties. And what we can do is, let's take a particular positronium state here, the triplet P2 state, and look at its ground state mass at finite photon mass, which is here 0.05, the mass of the electron. And then we'll decrease the photon mass and look at how the ground state goes. Well, until you get to about 0.03, you don't even get a bound state of positronium. And then the bound state becomes more deep as you go down here. Now, looking a little bit more at the details here, I mentioned Nmax, that's a cutoff. So 1/Nmax goes to 0, is taking that cutoff to infinity. And the discrete points are the calculated results. This problem is done in momentum space in the longitudinal direction. So we have a total longitudinal momentum quantity listed over here. So the discrete points are the calculated points. So what do? We take a set of these as a function of Nmax, and we look at the extrapolate, and they form a very, very linear behavior in 1/Nmax. So you can extrapolate them to infinite Nmax, and you can do that for each value of K. And then you can extrapolate K goes to infinity, because look at the patterns here. The patterns are very nicely converging as you go up in K. And there's a nice convergence plot you can make. It a nice polynomial form fits that very beautifully. Take those double extrapolations and plot the discrete points you've calculated, double extrapolated, as a function of the photon mass divided by the fermion mass. And your ground state, your triplet S1, your triplet P2 follow a trajectory towards mu goes to 0. Mu goes to 0 is the no regulator limit now. You've done a triple extrapolation. All your regulators have been taken out of the problem. So if you believe the curves here, which are simple functions drawn through the calculated points, you get a extrapolated result for the continuum treatment of positronium at strong coupling. And you can compare that with alpha to the 4th perturbation theory estimates, and you can see they're extremely close for these 3 states. You may say, well, what's going on up here? Well, like I said, the triplet P2 is not even bound until you get below a certain photon mass, but then it drops down nicely through the. Sorry?
Why the error is bigger in the ground?
Error is bigger. Very good question. Yeah. So I'm not quite sure to answer your question honestly. It's not much different. You can see a little bit more of a displacement. Yeah, you got a very good eye. Yeah, yeah. But error is perhaps not the right word, right? We're comparing a non-perturbative calculation with a perturbative The difference is somewhat bigger for the ground state. Now, I could wave my hands and say I actually think the difference should be stronger for the more non-perturbative solution. Right? The deeper bound the state, the more non-perturbative your solution is. So it's okay with me that it's a little bit bigger. Sorry?
As you go on the ground state, you have a small state, a smaller state.
Smaller state.
And then you can allow, I mean, according to the inceptical principle, the energy time to allow higher state. So it's more easy to mix with the time.
Yeah. So yeah, I think you're right. And you have higher momentum modes. Another way of saying it, I think, is you have higher momentum modes at play in describing this deeply bound state relative to the next state. Yeah. Good. All right. So this was our initial test problem and viewed as a big success. You can look at finer details, look at these extrapolations and study uncertainties in your extrapolations and a bunch of other numerical studies that can be performed. But anyway, now fast forward to the present. We still keep positronium as a fundamental test problem. And we'd like to do better. And for one thing, we can use it to study renormalization issues. How to do renormalization non-perturbatively. And that's the feature of an upcoming talk on Wednesday here by Jingbo Zhao. And in this problem, we're going to do things a little bit differently. We're going to actually have 2 Fock sectors, E plus, E minus, and a photon. So you have your Lagrange, your Hamiltonian will actually end up with what? It's going to end up with these 2 terms. A photon is emitted and absorbed by your fermion, and now you have this difficult to treat instantaneous fermion, notoriously divergent quantity, and requires renormalization, a renormalization scheme. So how does that scheme work? Well, first take a look at what the full Hamiltonian matrix looks like for fermion, antifermion, fermion, antifermion gauge boson. You would have these terms appearing off diagonal, this term appearing diagonal, and you're taught to not put any interaction here until you include more dynamical photons to avoid improperly counting balancing contributions. So that's the setup of the many-body problem. There's a mass renormalization procedure, which is followed. This is a version of what we call the sector-dependent mass renormalization. You take the single electron problem in the same basis space, and you compute the counter term necessary to give you the physical electron in the same basis space. And that then gives you the electron you're going to embed along with its partner, the positronium, into the full matrix problem we just looked at. So it's going to have a mass counter term involved. The mass counter term is small compared to the physical mass. By the way, this is all done at the physical coupling now, 1/137. Okay, so to short circuit this discussion and save all the thunder and lightning for Jingbo's talk, I'll just mention that if you don't put the renormalization in your ground state mass as a function of Nmax, just simply falls through the floor. You put the physical electron in the same basis with its mass counter term in the problem, and you get a nice convergence pattern for the ground state energy as a function of Nmax. There's some additional subtleties that are looked at to make this all work, and I'll leave that for him to discuss as a part of the overall renormalization scheme that they've come up with. Light front wave functions, you can look at those and see kind of ordinary, non-relativistic looking wave functions in the transverse plane for the standard spin components of positronium. And then you have your non-standard components coming from the relativistic theory, which are small and have very exotic structures inside of them. So relativity is always close at hand. It's suppressed for obvious reasons, but it's still there and visible. Parton distribution functions. Here's your photon inside positronium, the probability of finding a photon with a certain light front momentum fraction, and the probability of finding the electron with a certain momentum fraction. Even more recent, there's another renormalization scheme under development. I mentioned it earlier, renormalization group project for effective particles. Camille Serafin will talk about this also on Wednesday. And here the idea is that if you've renormalized in the light front scheme, renormalize your Hamiltonian problem at the level of, again, effective particles, similar to the spirit of what Jingbo Zhao will talk about, but following a similarity renormalization group project, what you get is, as a function of gluon mass going to zero, a sequence of energies for the ground state of positronium, which extrapolate nicely. When plotted as a function of cutoff, they become independent of the cutoff at zero photon mass and infinite cutoffs here. So again, that's kind of like our photon regulation we saw earlier, but now practiced in more careful detail to see what the electron and the positron are doing. Hyperfine splitting also becomes stable as a function of cutoff. So this procedure looks like it's working very well for positronium and has great promise for applications in QCD. So this is probably one of the few preferred procedures going forward for non-perturbative renormalization. Results to date show, for example, ground state energy at the physical coupling now, within 1% of positronium's ground state coupling, and the excited state spectrum converged and also within 1% of the expected value. Which, this here? Oh, go back to the previous slide. Okay. Yeah. That's photon. Photon mass. Yeah. Gauge boson. M gauge is some fraction of the electron. Yeah. Confusing, I agree. Okay, good. So now turning our attention to the hadron applications, mesons and baryons. What does that look like? Well, I can summarize a lot of the works that have been done and some of those that are ongoing now by just drawing your attention to what are some of the common features of these applications. So in most everything up to recent works that I'll talk about, we have a transverse confinement, which itself comes from the harmonic oscillator. So the harmonic oscillator transverse confinement There's a longitudinal confinement that's matching in some respects the transverse confinement, which has also been introduced. Our basis functions, as mentioned earlier, come from exact solutions of some reference Hamiltonians, so they have nice analytic properties. Wherever possible, we want to compare our results with, first of all, experiment. Secondly, any lattice calculations available, or covariant wave equation treatment, Dyson-Schwinger, beta-salpeter results that could be available. So you'll see a lot of the results are cross-compared with all of these other techniques to see how well they seem to be, how similar they seem to be. Okay, now in many calculations, we're still using the effective one gauge boson exchange. That could be the photon in positronium or the gluon in the meson. One gluon exchange has been introduced. To do our first treatments of the lightest mesons, we studied the Nambo-Jono-Lucidio model to invoke certain properties of chiral symmetry breaking. So that was a useful tool for us to get a feeling for how important chiral symmetry breaking is in light front quantized approaches. So our Fock sector truncations, initially for the first few years, all the work was in valence sector only. So QQ bar for the mesons and QQQ for the hadrons, the baryons. Nowadays, and more recently in the last couple of years, we have one dynamical gluon. And now at this meeting, you'll see some of the first results with C quarks and more. So that's a very exciting time we're at, where preliminary results are starting to emerge, where we're starting to expand the Fock sectors to include more fields, more partons inside of our proton or meson. Observables span the range of observables that can be conveniently obtained from lepton-hadron and hadron-hadron scatterings, as well as spontaneous transitions, electromagnetic or weak transitions. And we look at things like how the system behaves in external fields and non-perturbative ways, with a generalization to time-dependent basis light front quantization. So non-perturbative scattering problems now are also addressable by generalizing these techniques to the scattering in a time-dependent framework. Most recently, the last year and a half, 2 years, quantum computer applications of basis light front quantization have started to appear. And there's a huge appeal in terms of an ideal fit between something like basis light front quantization and quantum computing techniques. So this is taking off in a big way, all on its own, with computer scientists and others jumping into that set of applications. Okay, so the initial quark anti-quark problems were done with heavy quarkonia. The light front Hamiltonian that you would derive would have a kinetic energy term for the quark and the anti-quark. The phenomenological confining terms of ADS QCD form and the matching longitudinal confinement form are introduced with one single parameter governing the strength, kappa, as an intermediate step. We do this because we don't have enough dynamics to generate confinement, but we believe confinement is important for the infrared physics in the problem. So we're going to model it for the present time with a single parameter. And then you still have your one gluon exchange coming from QCD. So we put this all together, and you solve for the spectroscopy of the charmonia and the barbamonia. You have a few parameters, of course. Quark masses, confinement strength. You have a running coupling in here with an overall infrared regulated version of the infrared of the running coupling. And so the question is, well, how well can you do with a few parameters? And the answer is you can do spectacularly well for charmonium and bottomonium. The particle data group lines are red. The BLFQ lines are black. Any uncertainty due to angular momentum, non-exact angular momentum conservation is given by the box. And then various experimental results also depicted. So right on up through the known charmonium states, the known bottomonium states, there's an excellent lineup. If you look at this in terms of a table here, the charmonium states, you have a confinement strength, the mass of your charm quark, your RMS deviation when you fit to about a dozen states is at the level of 31 megavolts, and the bottomonium spectrum with its confining strength and quark mass is about 38 megavolts on scales of GeV. This is competitive with some of the best phenomenological models available. The basis Hamiltonian matrix dimensions are not very large in our term. A couple thousand dimensional matrices are involved. Now you have your light front wave functions. Let's go to work. No more parameters, please. We're off to the races just applying those to observables. So for example, what about the A to C decay width to 2 photons? Well, that's known according to the particle data group to be a value here right around 5 with small uncertainty. You have various calculations, lattice and others, giving you results of the width. And here's the BLFQ width, no free parameters. Okay, how about the chi sub c? A very similar story. Pretty good agreement between theory and experiment. To see really the good agreement between theory and experiment, let's plot one experimental observable here, the width, versus the hadron mass that you got out of your calculation. And then you have a particle data group point indicated by the star and the BLFQ point indicated by the diamond. And to make it easy to see this, I drew little circles around the correlation between theory and experiment. And there are other results from other approaches peppered around, but none of them seem to be as close to theory in between.
Why is the chi sub c, the chi sub c 0, so much worse than the chi sub c 1 and chi sub c 2?
So much worse. You call that much worse? I'm ecstatic by that agreement, but you, okay.
No, but the errors are much bigger.
Okay, so all I can say is, oh, you mean why are our errors so much smaller? Ah, so much bigger. Okay, so this error comes about by studying things like the basis space dependence of the calculation. So if we vary Nmax and retune the parameters the way we did it, how much a difference emerged? And it turned out chi sub c was more sensitive to that. Now, that could be a number of things going on. Maybe the mixture of higher Fox sectors is playing more of a role. That would be a speculation on my part. Okay, good question. Hey, we have people looking at the details on these slides. My goodness, that's great. All right. All right, so more observables. Again, no free parameters. Here's the 2 photon decay of the eta sub c, but now look at the entire form factor. There is actual data to be compared with, and this is the no free parameter calculation from BLFQ. Now, some people like to use an approximation called the distribution amplitude approximation. That turns out to be a bad idea because the actual more direct calculation without that approximation shows pretty good agreement with the experimental data. So more observables. Well, before we get there, let's take a look at the landscape of what we're facing. So we would ideally like to have our Fox spaces grow over time to include more dynamics. So for a meson, we not only include the dynamical gluon, but we include things like multi-gluon configurations, C-quark distributions, and so on up the ladder. Baryons, a similar story of growing your partons that you allow into your bases. Well, let's even think a little bit about real nuclei like deuterium. After all, that's going to be a beam at the EIC. We would like a good description of deuterium at the quark-gluon level to begin to talk about modifications of inside the medium of quark distribution function of all sorts. Well, you in principle have access to that. If you have a a many particle framework where you can control all the symmetries and study the numerical convergence properties, why not? And then you're off to the race. Well, the problem, of course, is size of the calculation. If I take a meson, a baryon, and a deuterium, and I ask, you know, as I increase my parton numbers at fixed Nmax and fixed longitudinal momentum, how does my basis space grow? So these two are fixed. The parton numbers go up like this. The dimensionalities are increasing exponentially, or nearly so, and you're quickly up to a billion by billion matrix or higher. So these become daunting numerical problems, and all sorts of challenges will emerge. But let's forge ahead. Maybe quantum computers will solve all of that for us. Who knows? Now let's go to treat the mesons again, but now with the dynamical gluon. And this is work which will be talked about by Zhongshan Lan tomorrow. He'll show how with available parameters, he can fit half a dozen low-lying meson states and predict some others. That's the red dashes. And if you look at the decay constants that emerge from fitting the spectroscopy, they're not too bad. You know, they're aligned with the trend that you expect from experiment, not perfect, but still moving in the right direction. So not a bad story, considering you're only at the moment including just one dynamical gluon. Okay, but once you've done that and got your light front wave functions, you can begin to address things like J-psi production cross sections. So here's a plot comparing with CERN FNAL data, different targets: beryllium, proton, lithium, pion nucleus Drell-Yan cross sections. Data in green. The total BLFQ result is the highest line, summing over the different components that contribute. So basically, you find a significant contribution coming from gluon-gluon fusion, which should not surprise anybody. You have data over wide ranges of bombarding energies and different targets, all looking good in terms of agreement with the experiment. Input here is the CTEC distribution of the nucleon, but the pion comes from BLFQ. Okay, so this is a very encouraging story. Yes. Yeah, in principle, yeah, for sure. Okay, vector meson structure will be reported by Satya Kaur on Thursday. Her work looks at the rho meson and extracts various parton distribution functions for the gluon and the quarks, and gives you some uncertainty band based on theoretical analyses. So stay tuned for that. So now we upgrade to baryons with one dynamical gluon, and I'll start to go a little bit more quickly because I want the most exciting part to be coming up here in terms of previews of some of the forthcoming announcements at this meeting. Okay, so we still have confinement. We have the interaction from QCD, but one dynamical gluon. And here, what we find out is, let's take a look at the unpolarized proton distribution functions. First of all, take a look at the global analyses, JAM and NNPDF. There's the gray band for JAM, and the NNPDF is the pink. And the gluon distributions are all divided by 10 to get them on the same scale. What's interesting to note here is a trend. Without dynamical gluon, we find our best initialization scale is lower, and the gluon distribution resulting after evolution to 10 Jev squared is way up here. You put in one dynamical gluon, refit the initialization scale to some moment of some distribution, and then QCD evolve it, and you get an improved gluon distribution. So even putting in one gluon gives us a trend towards better agreement with the phenomenological, or sorry, the extracted global fits on the gluon distribution. At higher X, there's not much differences to talk about, or maybe the up quark depletion here at some modest value of X is yet to be understood. Down quark is not too bad, but the general orders of magnitude are all looking pretty good. And then, of course, ratios up here, the trend is also favorable by putting in the dynamical gluon to get towards better agreement with the down to up quark ratio as a function of X. So again, stressing no, well, I should qualify that. There's no parameter adjusted to this data. These initialization scales have to be determined by looking at some other observable, which we do, and that fixes it for us to within some uncertainty. And that's the uncertainty bands that are drawn here for the output. Okay, so helicity, in order to save time, I'm going to go through quickly things that will be available from Shandong Mondal's talk. Helicity parton distributions look pretty good overall, where there are no, well, there's some data, and you get predictions for the gluon helicity distributions and some others, which hopefully data will get better over time, and based on the EIC promises, we can expect that. Asymmetries, helicity asymmetries look pretty good also. General trend, the BLFQ is up here. Let's see. The blue, it's still the blue. That's right. BLFQ, that's right, right here. It's still the blue. Okay. Right. Yeah. It's quark model like. Yeah. Good. Okay. Gluon GPDs are obtained, and these are the skewness equals 0 GPDs plotted, available for comparison with other frameworks. What's interesting to note here is the gluon content of the angular momentum is only about 13% for the proton of the total angular momentum of the proton, which because you only have one dynamical gluon may not be a bad thing. It'd be interesting to see how this changes as you put more dynamical fields into the problem. How about the spin decomposition of the proton? If you take delta sigma, it's a Q quark part. You're going to get 72% from the calculations we've done. And then depending on your scheme, you get a breakdown as delta sigma for the gluon, about 25%. And then the so-called canonical orbital angular momentum, only about 3% here. Or if you go for the kinetic orbital angular momenta, you get things like 17% and 17% for the quark orbital angular momentum, and JG, the gluon spin content, is about 11%. So these numbers are obviously not in agreement with the experiment, because you expect this to be around a half or lower, and these other quantities to take over. But obviously we're not there yet. This is a limited basis space, and probably that's the source of the difference at the present time. Gluon transverse momentum distributions also available. Here there are various bounds that you can check that you expect to be found with these momentum distributions, then they are all obeyed properly. Okay, gravitational interactions with baryons, with hadrons in general. We have a couple of recent works here to refer to. Zheng Chao on Tuesday will talk about quantum stress on the light front. And among many things he'll be showing is how in a model scalar nucleon with the physical mass of a physical nucleon and a pion mass of a physical pion, you're able to extract the fact that the matter radius differs from the charge radius substantially in this model problem. And that kind of difference, now maybe not that magnitude, but a significant difference between matter and charge radii may be expected in the physical hadrons as well. Okay, then Satir Nair will talk about Sriraj Nair will talk about gravitational form factors of the proton, where you actually take some of our wave functions, which have been calculated, and extract the gravitational form factors defined here, and plot them up and compare with other methods. Lattice methods are compared because they're available. And in general, there's similarity between our results and the lattice methods shown here. So quite a bit of information content here, I know. If you look at comparison again with lattice, but also the Herculean effort to extract information about the D form factor from JLab CDIS data, right? SIDIS data, if I remember right. You see that that data is sprinkled in here, and that's at a scale of 4 Jev squared. Well, we know our scale is not that high, so let's make the assumption we can evolve our structure functions as we do for other structure functions. Big bold assumption, and you get down here in that same ballpark, but that's just an assumption. Okay. Now here comes the final big step forward. Yeah. This one? Yeah, it's based on that. The meson final states, as I recall. Yeah, massive final states, yeah. Okay. Perhaps you can ask our colleague, Sriraj, in more detail. Okay. Oh, DVCS. Which involves some assumptions, right? Great. Okay. Now the big story forward, which will be presented by C.G. Xu on Wednesday, is now up to 6 Fox sectors in his most recent calculations of last week. So you can see the C quarks, and you can also see 2 gluon added into the 3 quark system. And now let's drop explicit confinement. So let's say we hope we're on the track to actually have fewer parameters where the confinement is no longer has to be assumed, that we're getting enough of the infrared physics from the dynamics. And so we'll omit confinement, and we'll, again, as mentioned earlier, have factorization of internal motion from center of mass motion by a Lagrange multiplier term added to our Hamiltonian. But at this stage, one encounters some of those other processes that we were referring to earlier. Not all time orderings were shown in the earlier version, so this is just a different time ordering of, these are different time orderings of different graphs that were shown earlier. But all these processes now enter the calculations. And just a kind of a 1,000 feet up or 30,000 feet up view of what's coming out. The leading Fox sector, 3 quark piece of the Fox space is about 75% of the proton. You have the single gluon pulling in another, the single dynamical gluon part with the 3 quarks pulling in another 23%, and then very small C quark and 2 gluon components, percent or smaller in the present calculations. And just to give you a look at some of the computational complexity that's happening, we said earlier, we only keep global color singlets. So how many are there? Well, for that Fox sector, there are, every space spin configuration has 3 color singlet states. Here, every space spin configuration has 6 color singlets. So your basis space grows very quickly, and even at modest n max and k, the matrix dimension is approaching 400,000 by 400,000 dimensional matrices. So we're getting up there now. About what?
Intrinsic charm.
In principle, yeah, it's very small at the moment, but no, sorry, it's not included yet. So we can't say, no, not explicitly, but in principle, we could put that in as another version of the C-core contribution, but the expectation would be it would be very small, unless something dramatic happens, which is coming from the couplings in the problem. But what would that be? I guess my question. But yeah, definitely worth looking at. The up and the down, yeah. So at the present time, yeah. So at the present time, the quark masses are large. Coupling constant is also large, you'll notice. So this is what gives the fit to the spectroscopy, the mass of the proton and the low-lying baryon states in this the basis with no confinement. So there's a whole bunch of things that have been changed. Now, this is preliminary, but may not be the end of the story. And ultimately, we wouldn't want to do fits anyway. We'd rather do this RGPEP treatment, which will tell us what the mass of the quarks should be for this basis space. That we haven't, that would be the longer term view of what we should be doing. So consider this as a very, very early step in the game and taken with a grain of salt. Parton distribution functions are emerging, looking reasonable for the C quarks and the valence, the ordinary up and down quarks and the gluon. Okay, since I've basically run out of time, I'm just going to pass over the time-dependent basis light front quantization work. Some beautiful work has been done on scattering, looking at jet propagation through color glass condensates and looking at the jet broadening by the same techniques that we have been showing, but now using those Hamiltonians that time evolved the system through a medium and looking at the non-perturbative evolution. So some beautiful work. It's ongoing in Europe and here. As I mentioned already, and I can kind of go over this quickly, this is all set up ideally for a framework suitable for quantum computing. First publications have emerged where you solve for the ground states of the mesons using something called the variational quantum eigensolver approach on quantum computers, now published last year, and a host of other applications are underway, just showing how to do these problems on quantum computers. Your Hamiltonian, by the way, begins to look very strange, but that is the same Hamiltonian we've been talking about, viewed in terms of Pauli spin operations on qubits. Okay, just another comment about the available talks here. Tuesday, Wednesday, and Thursday, I've featured highlights from each of these talks. They'll go into considerable detail, happily answering, I'm sure, the questions I couldn't. So please stay tuned for additional important results. I only have a very tiny amount of their results. So where are we at? Okay, so having proven that you could do problems like QED problems in a non-ideal basis choice, we have techniques set up. We have renormalization schemes that seem to work. We have regularization and extrapolation tools that seem to be working. So we are off to the races now, where the big plan now is to continue to expand the Fock spaces. We have a lot more work to do on the renormalization schemes. We'll continue that. Behind the scenes, a lot of work has to be done to make sure you're using supercomputing resources efficiently. We're rapidly approaching the stage where we have to compete with lattice gauge theorists for supercomputer time. So we better have efficient codes to do that. And at the same time, a host of others are joining this kind of line of investigation because it's ideal to have a Hamiltonian framework, which is very ideal for quantum computers. So with that, I thank you for your kind attention. I thank the students in Ames, Iowa at Iowa State University for your patience listening to this online today. Thank you.
Thanks, James, for the very nice lecture. Any questions? Okay.
I was wondering, you mentioned the three ways of quantizing theory, the instant light front and the point form. What's the advantage or disadvantage of the last kind, the point form? Is it used for anything or it doesn't?
Some people claim it is. The algebraic framework looks a lot, again, like non-relativistic quantum mechanics of many body problems for the angular momentum algebra. I know we had a colleague at University of Iowa where Wayne as his position, it looked at that for a number of years, but I don't think it got to the computational application phase. Okay. A lot of theoretical work on it though. I'm still working on it. Okay. Okay.
Any questions? Any other questions? Okay.
You told that you calculated in Light-Cone gauge, but in principle, off-shell kernel, which enters in calculations, can depend on gauge. And have you compared your results with numerical results for eigenvalues for these other gauges?
No, we can't. Hopefully somebody else will come along and do a calculation in another gauge to compare with. But we made a choice early on. We have enough headaches trying to keep that one going.
Suppose that it will be different to some degree.
It would be nice to know what would be the advertised difference from the start. You know, what would be the advantage of another gauge, you know?
Alphonse.
Thank you for the very nice lecture. At some point you show an effective Hamiltonian, and it had some kinematic part, then some confinement part. That was some kind of a two-dimensional harmonic oscillator. But I wonder, how can you see that kind of Hamiltonian would arise from the QCD Hamiltonian?
That's a good question. Yeah, so our hope, and it's really just a hope, is now we're engaged in removing that term, and we hope to be able to see quality agreement between theory and experiment improve as you expand your Fox sectors. The belief or understanding is that you have to get the infrared physics, the long range physics, right to get your spectroscopy to work out, as well as many of your other experimental observables, which are sensitive to infrared regions. And that can only happen if you've got some sort of long range effective interaction arise. The effects of long range physics have to be built from multiple interactions of particles within the standard QCD and QCD vertex structures. So,
right, but in order to get the other terms, you also did some kind of truncation, right? On the original QCD Hamiltonian.
We don't truncate the Hamiltonian anymore. We're rapidly approaching the point where all terms in the Hamiltonian are present. There's still one more term that will be incorporated when you get one more, the gluons in with the C quarks. And then you'll get, is that it? The gluons, yeah. One more term will be in there. And then we will have the complete set of QCD terms.
Right, and you expect the emergence of this kind of infrared.
Oh, that would be nice, right? That'd be a big hope.
Okay, thank you.
We'll see.
Okay, any question? More?
You have one down here.
Okay.
We know, I mean, that the quarks and gluons have their internal dynamics. So they are not fixed mass. No, they are not particles with fixed mass. No, these masses, as we see from lattice QCD or Schwinger Dyson, they run with the momentum.
Yeah.
Can we incorporate in the scheme?
But that's the hope that the RGPEP approach, as well as the approach that Jingbo Zhao uses. So just to relate that to your point. So there's a set of modes we're going to solve the problem in. Within that set of modes, we could calculate the renormalized mass that gives the physical mass of a single electron, for example. And that's what Jingbo Zhao does. Also what Camille Serafin does. He's not here yet, but that's what he does. Now, for the quark problem, you also will have to establish some reference point for the quark, renormalized quark mass. And since they can't get a free quark, that's going to be a little more challenging. We have to think about what experimental observable are we going to pick to tell us what is the quark mass for that scale in this set of modes. But that will run. That will certainly run as we move up the scale, then it'll be a different quark mass. So will it run as we naively expected towards a current quark mass as you would keep increasing the scale? Good question. We don't know. We'll have to watch that.
Okay.
I think regarding the quark mass, in principle, one has to solve so-called the mass gap equations, right? Yeah. So that really interesting question is what's the time-like behavior of the mass gap equations? And I think in the form factor calculations, I think one of the advantage of the electron dynamics is to cover time-like and space-like together.
Yeah.
So there is a way that we can calculate the entire range that couldn't be done with the lattice QCD or dimensioning, etc.
Very good point. Very good point.
Okay. Any more questions to James? Okay, so now we have a cocktail. 1 minute.
Just one reminder for the speakers of tomorrow morning, if they have not sent yet the PDF or PowerPoint of their talks, please send to rogerio@cbpf.br and Light-Cone 2023 @gmail.com. Okay, then we can go smooth in the morning. Thank you. So now let us enjoy the cocktail.